Rob, we are about to get started. Good morning, everyone. My name is Eric Ciccaretti. I'm an advisor in the Office of Technical Reporting and Economics. And I want to welcome you to the Technical Conference on Increasing Market and Planning Efficiency Through Improved Software, the Software Conference, in FERC docket number 8010-12-17. That 17 means that we've been doing this conference for 17 years now. Each year, the conference brings together researchers and experts from a broad range of expertise to talk about software. It's a chance to share research on how software can improve the workings of the electric grid and the electric markets, how to make them more efficient, more reliable, and more affordable. I wanted to open this year's conference because this year we're taking a different approach. Previously, this conference has discussed a range of software presentations for 2 days. This year, Chairman Sweat asked us to do something a little different, to focus on 2 topics, grid enhancing technologies, GETS, and load forecasting, which we'll do today in two separate panels. These 2 topics are timely because in different ways they address the challenges that the grid faces today. Grid enhancing technologies make better use of the existing grid, reducing costs and improving reliability. Accurate load forecasting can ensure efficient planning, construction, and operation of the generation and transmission needed to serve increased load. On the second day, tomorrow, we'll return to our regular programming, discussing software to discuss the challenges facing the grid, including optimization of storage and other resources, grid planning, and even more on load forecasting. For both days, we want these discussions to be timely, but as a reminder, we will not be discussing pending proceedings before the Commission. The honor of welcoming you to this conference entails the duty of detailing some of the logistics for the conference, starting with the schedule. Today, our first panel will discuss GETS. It will begin after my remarks and conclude at 12:45 p.m., and we'll call a break at the appropriate time. At 12:45, we'll break for lunch. We'll resume at 2 p.m. for our second panel on load forecasting. That panel will run till 5 p.m., again with a break. Our panels today will not have audience Q&A. Tomorrow, however, the presentations will. Both days of the conference are being webcast, which will be found on FERC's YouTube channel, and a link to the webcast will be found on ferc.gov on the Commission's calendar of events page. The conference will be transcribed, and the transcript will be available in the Commission's e-library under docket number AD10-12-17. Transcripts will also be available for a fee. For those present in person, a few housekeeping items. Today and tomorrow, the conference is in this room, the Commission meeting room. As you've learned, to enter the building, you'll need a real ID or a passport. Security has provided each of you in person with a badge, and they are required to be worn at all times and required for re-entry into the building. No food or drinks other than water are allowed in the Commission meeting room. Water fountains and restrooms are available by the elevator bays on this floor and the first floor. On the third floor, snacks and drinks are available for purchase in the public canteen by the west elevators. Also, there's coffee there. Before starting the first panel, on behalf of the Commission and my colleagues on staff, I want to thank the panelists, tomorrow's presenters, and the attendees for joining us today. In particular, thank you to the panelists and presenters for the work you've done to prepare for this discussion and for the work that underlies those presentations. I now turn to my colleagues, Jesse Hensley and Stefania Moss, to start us off with the first panel.
Good morning. Thank you for being here. My name is Jesse Hensley. I'm a Senior Market Advisor in the Office of Technical Reporting and Economics. I'm joined by my co-moderator, Stefania Moss, and other staff members. So this panel is the GETS panel. It provides a public forum to discuss the opportunities and challenges associated with successfully deploying grid-enhancing technologies, barriers to their implementation, and then advances in the development of emerging GETs and related software. As Eric said, we don't intend to discuss any specific proceedings pending before the commission, but if a topic comes up where we're getting close, staff, myself, or others will unmute and let everyone know. So thank you once again for being here, and I'll turn it over to Stefania.
Thank you, Jesse. My name is Stefania, and I am an energy industry analyst in the Office of Technical Reporting and Economics, and I will be serving as your co-moderator today. I wanted to take a moment to introduce our panelists. Starting on my right, we have Dr. Alexandre Parisot from Linux Foundation Energy. Next, we have Andrew Schneller from National Grid, followed by Alex Watkins from Southwest Power Pool, David Quier from PPL Electric Utilities, Emilie Tullis from LineVision Inc., Michael Craig from Great River Energy, and Saugata Biswas from GridAstra. Thank you all for joining us as panelists. We are very excited about today's conversations. Before we begin our discussion, a quick process note. If you'd like to respond to any of the questions that we'll be asking, please place your name tent on its side to indicate that you'd like to respond to anything. That will signal to us that you want to respond, and we will call on you. To unmute your microphone, press the button, and if it's green, that means it's on. If it's red, you are muted. Please remain muted if you're not speaking so we can reduce background noise. And with that, I will turn it back to Jesse to kick us off.
All right, thanks. So question 1, what do you view as the main challenge in deploying GETs? And then what software improvements could address these challenges, or what existing software has the potential to do so? Anybody? Lively group. Looks like Emilie's going.
Yeah, if it's easier, you could do that as well. Whatever works.
Thank you.
So representing LineVision, specifically dynamic line ratings, the challenges we see really are more, I'd say, institutional than technology. I think starting with the implementation of hourly ratings, which really ties back to FERC 881, the implementation of AAR, that's a big challenge for operators. Being able to change, from an annual or even a seasonally adjusted ratings to something that is hourly, it adds a lot of variability to their ability to plan. So even though there is the promise of more accurate ratings and more real-time information, it's just a really big adjustment and it has a lot of ripple effects. I think the other component is really figuring out how to integrate into regular operations. So we have seen the greatest success where we are able to be EMS integrated and actually be in the control room and be part of kind of the regular cadence of data versus, what we call maybe a swivel chair integration where somebody is manually entering the ratings. I think the adoption and the effectiveness of that information and the value of DLR is kind of reduced when it's not part of those processes. And that takes a significant investment to kind of get over the pilot hump and get into a really operationalized process.
David, thank you.
Thank you. I agree with what Emilie said. It's one thing to put sensors on a line. If you take dynamic line ratings, take back data and calculate a rating. It's very straightforward. If you think of the sensors, they're taking relatively simple measurements: ambient temperature, conductor temperature, vibration or sag, wind speeds. You're taking those data points back, and now based off of what that conductor type is, now you're calculating a rating on a continuous basis. Taking that back to an engineer on a desk or even just displaying in an operating center is pretty straightforward, but doesn't really get you all the benefits that you're looking for your customers. The challenge is when you're trying to take that data and that calculated real-time rating and now plug it into, say, the day-ahead market that affects congestion pricing, or leveraging that data to defer or eliminate the need for a transmission project. In order to make that connection, for us at least at PPL and our Pennsylvania utility in PJM, the hard part is really working with the RTO to really pull that thread all the way through. So just like Emilie said, you have to take that data, you have to incorporate it into your operational flow of a calculated rating. But then you have to keep pulling it through in that instead of sending static ratings, for instance, for us between PPL and PJM, now you have to work with PJM in order to get pretty much that same stream flow of data so that not only are we getting a dynamic line rating, they are, and then they could incorporate it into their basically day-ahead market pricing and then account for it in their modeling for our type projects. And so for us, and I can give the specific line, it was the Harwood Susquehanna line, we were able to defer an over $50 million rebuild with a dynamic line ratings project that was several $100,000. And the way that is able to work is very close coordination within PJM, the RTO and PJM. And then just to talk about how we were able to pull it into the day-ahead market, you're relying on, say, PJM to also calculate things like assumptions and building an API between our software, our operational software, and their own. So in order to get it off the ground, we basically met with PJM every week, IT group to IT group, engineering group to engineering group, and we worked on every issue for about a year in order to pull that simple operational data all the way through to where it could actually save customers money. From the time we decided to put the sensors up, it was just a few months. But from the time you actually make it fully operational, where it can actually connect to market prices, that's where most of the legwork is.
I know we've spoken before, David, but remind me, how long have you had DLRs on your system?
So at this time, it's about 4 or 5 years, somewhere in that time frame. We've continued to add every year in our Pennsylvania territory, and we now have also rolled DLR out on several voltage levels in our Rhode Island territory.
Yeah, thanks again. I saw Saugata next.
Thank you. So I'm representing GridAstra here. So when we talk about GETS,
Oh,
Broadly-
can you put, yeah, oh, there you go, thanks.
Thank you so much. Yeah, when we talk about GETS, we are essentially talking about multiple different technologies. So DLR is like one of them. Power flow controllers is another one. Topology optimization is another one. And then even advanced reconductoring can be considered as an alternate transmission technology, or GETS. So one of the challenges, if you look at it from a broader perspective, is a lot of these technologies, let's say topology optimization or power flow controllers, I mean, you need to actually plan the grid to have these kind of things in operations later on. So it's a planning problem and it's an operations problem both. And if you do not have the software that can actually model these different types of grid enhancing technologies that I just mentioned and figure out the impact of that on a system-wide level, because the power systems is a non-linear system, it's a macroscopic system. You do something here, the impact will be somewhere else. How do you kind of evaluate those impacts of the GETS? And then figure out that it's not just about modeling the GETS, it's also about optimizing the grid using different types of GETS and coordinating all these different types of GETS and get a combined win or a combined impact. Now, how do you do that in planning? And then how do you do that in operations? And that is where what I strongly believe is, that is where software plays a big role. If the conventional software does not have the ways to model these, and not just model, but also to optimize different types of GETS and coordinate each of them and find out the different permutations and combinations of the solutions, that's a missing piece right now that I feel should be filled up. I mean, if the software can be looked more as a decision support mechanism in both planning and operations, I think the adoption of GETS can be broadly increased. So I think that's a missing gap that we see as well. And that's where GridAstra tries to play a big role with the kind of software that we are trying to have.
Yeah, thanks. I know that's a blind spot for me too, is how it moves from like the owner or operator to the grid operator. And that's maybe a good segue to Alex from SPP.
Yes, sir. So I'd say from our perspective, not being an RTO, reliability coordinator, things like that, not the actual utility, implementing a lot of GITS. We support a lot of our utilities in it. Definitely try not to be a barrier, but spanning the two different interconnects, we've seen utilities with varying levels of interest in implementing different technologies, and you really hit on what I was going to touch on is as you apply various GITS, whether that be dynamic line rakings, on top of topology optimization, on top of remedial axial schemes, on top of phase shifters, you start to get a lot of different levers that you can pull that you can't think of in a silo. They all impact each other, particularly if they're all in a region together. So applying not only that in real time and maintaining situational awareness, as your topology changes, as you're applying multiple different dynamic things at once, also applying that into your operational planning, looking at outage coordination, looking at the next week out, the next month out, even into your short-term, 1 to 5 year planning processes can be a challenge just because you're applying layers of uncertainty. Now, with that complexity comes a lot of benefits, obviously. You just have to account for it.
Thanks. I think we'll go down the line. Andrew, and then Alexander, and then Michael Craig, right? All right. All right, thanks.
Thank you. So first, I just wanted to say thank you for the invitation to participate in this panel. I really appreciate the opportunity. So we're really excited about GETS and the opportunities they offer for getting customers connected, increasing supply on the grid. National Grid has service territories in New York, Massachusetts, and New Hampshire and Vermont as well as in the UK. And what we've seen is that the applications for some of these things are different depending on the service territory and the particular challenges that you face in those different areas. So, for example, in the UK, it's a very congested system, and by adding DLR, you can very quickly decongest the system and get a lot of quick, easy to identify economic benefits. Whereas in New England, for example, it's a smaller system and it's not nearly as congested, so it's a little bit more difficult to justify the benefits because it's not a specific, easy to identify economic benefit. But we've still found that there's absolutely benefits in terms of the operational flexibility that these technologies offer. It's just harder to quantify, and there isn't really a great framework for bringing forward something with those sort of more abstract type of benefits. So I'm talking about being able to maybe extend an outage while a backup line is out, or have a longer construction window and shorten the time frame to build something and maybe bring down the overall cost of a construction project. So those are some of the benefits that we see in our service territory. And so I think there's a challenge there with, how do you quantify those sort of operational benefits? But we've been deploying DLR, for example, since 2019. We've also got power flow controllers on our system, as well as StatComs and I guess I wanted to reiterate something that Ms. Tullis said, which is around the integration. So another challenge, I think your question was around, what software improvements can be made. So integrating to our EMS system is really important. It's if we're getting, for example, feedback from DLR about what's the rating on a line, and then they have to flip over to their EMS screen to see what the system is telling them is the rating, and then compare the two and make a decision. It's a lot less useful than if the systems are integrated and it's all on that EMS screen, and the control center operators can really use it. And I think, utilities are in different places with their EMS systems, right? So we're currently upgrading ours to a much more modern system. We've got one that we've been using for over a decade now, which may not integrate as well with some of these. So those integrations, I think, are critical. Thank you.
Good morning, everyone. So thank you a lot for organizing this panel. I come from a little bit of a different perspective, of course, from the Linux Foundation Energy perspective. So I'll describe this a little bit. So Linux Foundation Energy is a nonprofit that is dedicated to hosting and facilitating large-scale open source projects. So when we're talking about open source, we're talking about things like Linux, the operating system. We're talking things about Kubernetes, PyTorch, a lot of the things that are basically the building blocks of our technology. And open source has been changing a lot the way we actually do software. It's brought a lot more interoperability, modular solutions, speed of implementations. It's brought a lot of things around collaboration. So all industries essentially building together common solutions to common problems. And the reason why I'm saying that, if you indulge me, is because it actually resonates with a lot of what we heard here. I mean, so to me, the main barrier to the deployment of GETS is software integration. Deploying the hardware itself is not so hard, and it actually works. And I come from this also from a European perspective. I did most of my career in Europe. A lot of things that were described here, European utilities and the system operators are essentially exactly in the same place. So what struck me is we have a situation in which we need to improve software integration. We need to have better models. We need to make different systems, your operating software, your planning software, your outage management software, all work together. And so this we need also better models, because you need to, as was said, there are very different kind of GETS. There are very different ways to do DLR. And so in this situation, actually, what I would argue is this is a fantastic place to use these open source collaboration techniques that I've described, that have been very efficient in many other industries, such as telecom, healthcare, automobile, where people come together. A lot of the struggles that you describe, a lot of your peers actually have this as well. Vendors can actually collaborate, and we can all facilitate essentially the deployments of GETS across the system by making it easier for these components to be integrated into all of the softwares that we use. And we can illustrate that a little bit down the line, but for me, really the question of software integration is the key question, and I strongly believe that doing software differently, doing software in a modern ways, using some of these open source techniques that have been used across multiple other industries and to great effect, I think is a key component of integrating GETS into the system.
Maybe just a follow-up. I know you're representing open source, but one of my questions is, who owns that data? Is it the utility, the grid operator, the vendor, or all the above?
So when we talk about open source, we talk about the software code. And so the open source is actually owned by everybody. Essentially, one of the reasons of doing projects through the Linux Foundation is we operate as a neutral place for people to bring their code and put it together in a way that is accessible for everybody to use, to modify, to adapt with open governance. And so basically, it becomes a public good in a sense. And so which is actually fantastic, because that means everybody can use it. If you don't like it, you can modify it. You can share your modifications, and so you're ending up with software that's co-constructed by everybody in this open manner.
Yeah. Thank you, Michael. Thank you.
Thanks for having me. So I'm Michael Craig, and I'm representing Great River Energy, which is a cooperative in Minnesota. And we have about 1.7 million people, and we're mostly rural. So we're in rural Minnesota, so it's a little bit different. We've had DLR for about 3 years now. We've done distributed acoustic sensing. We've done some advanced conductoring. So we've kind of tried different things. I guess I would say for the challenges, for us, whenever we're looking at these grid enhancing technologies, we're always trying to find value for our members, and we're trying to make sure that it makes sense. So everything we do is for our membership. So when we're looking to deploy grid enhancing technologies, we have to have kind of a solid reason and business case for doing so. So one of the biggest challenges we have when we're looking at it is trying to model how a grid enhancing technology would affect our system economically and also for reliability, because it's kind of both sides. So there's different softwares that do that. I think we're going to talk about that a little bit later. But when we're looking at congestion, we're always looking at where is it congested, what's the impact to Great River Energy, and kind of what's the impact to the market in terms of economics. So that's kind of one of our considerations. We're very integrated with our neighbors in Minnesota. So there's XL Energy, Minnesota Power, and others up there. And so another consideration is when you're looking at this congestion, you need to make sure it's actually relieving congestion and not just moving it. Because if you kick it to the next line, you still have issues. The other issue is that dynamic line ratings specifically are usually for conductors, but facility ratings include the whole facility. So if the conductor isn't the limiting element, so meaning that the substation there is actually a limiting element, doing DLR on your lines actually won't generally get you any additional capacity. So I feel like there's a lot, I guess, about the planning side of it. You really need to know sort of where you're going to do it, where it makes sense. And that's kind of how we've looked at it. So we've had lines where the conductor is a limiting element and it would make sense, but the facilities are actually or I guess the conductor is limiting, but the facilities also would be limiting. Or we're integrated with another utility and we don't have any say on how they upgrade their system. So we can suggest things, we can call them and say that, but it's really up to them. The other thing I think that we found is it's sort of a culture shift in getting people to believe that grid enhancing technologies are the way to do it and that they are going to provide benefits, and that you really need to have a way to sort of prove that. Because I kind of spearheaded a lot of the programs at Great River Energy, and all the questions after the fact are, okay, how do you know it's working, and how well is it doing, and was it worth it, and should we keep doing it? Very, very basic questions from very utility looking to make sure we're providing value for our membership. So we have good support there, and it worked out well, and we were able to do all these things. But there are a lot of people who have done things the same way for a long time, and it's probably time to move on to whatever this next thing's going to be. But you have to convince people that that's going to be the case. The other thing I guess I'll just quickly echo is the integration part is also huge for us. We have integrated back to our EMS system, and we are setting ratings to MISO. But without operationalizing the data, it's really more of a research project. And so for us, we really want to, when we set forward with our projects, our goal was to get this to the end, to get it, we're actually using it in decision making and congestion relief and reliability. So the integration was a big part, both with EMS externally, but also with our internal systems. We have asset databases. We have a way we're doing line ratings. We've been doing line ratings for a long time. So when you say, okay, well, now we're doing dynamic line ratings, that changes sort of the flow of everything. So you really have to make sure that everything's working. So some softwares are better than others at integrating, but I think I'll leave it at that for now. So
Thank you. We started with Emilie, and maybe we'll close question one with Emilie.
All right, so this may feel a little bit out of left field, but one thing I wanted to touch on in the challenge is the accuracy and availability of CEII data representing the transmission grid. So that's actually been one of the longest poles in the tent for deploying DLR. We can basically deploy DLR in as little as 2 weeks once we have accurate data. I won't say who, but we've had utilities digging in filing cabinets to try to find paper drawings that they then have to upload. We've had many instances where we are doing cross-checks with Google Earth and ArcGIS, Open ArcGIS data, and finding errors or discrepancies, and then utilities are saying, oh, you're right, this is actually 5 meters over, and we didn't have that represented in our data. So the accuracy, the availability, and I think another burgeoning challenge is the security of that data, and making sure we as a vendor are not opening up a vector of attack for this incredibly sensitive data. That tends to be kind of an unexpected challenge as we're onboarding new customers that it's not necessarily accounted for in that kind of speeded power framework.
Thanks. I'll turn it over to Stefania.
Yeah, so several of you have talked about standing up your process for deploying GETS or your work with other companies or RTOs that have been doing it. I'm interested in knowing about if you have any key lessons learned from utilities or other system operators when they're exploring GETS deployment. And now that some of you have GETS on the system, I just want to see what were some key lessons learned from that process. David?
Some of our initial concerns were things like, we're obligated to comply with NER compliance. And so there's several standards that dynamic line ratings could affect, like FAC 08 line ratings, some of the SIP standards, et cetera. The other thing that we started when we started to list out any concerns that we needed to overcome were also things like, okay, these are ratings that are going to affect how we operate the bulk electric system. What happens during a gust? What happens if the sensor doesn't work? All of the kind of like those like worst case scenarios. So when we listed those out, the best way to approach them was really directly and pulling in the stakeholder that we maybe had the most, I'll use the word fear of, for lack of a better immediate term. So for instance, take the NER compliance standards. We were thinking through when we were going into an audit, how are we going to comply with FAC 08 with lines that have dynamic line ratings on them? Because when you kind of match it up, it kind of doesn't necessarily match with what we're doing. So we pulled in reliability first. They were excellent. We requested an assist visit, and we worked through every NERC standard that dynamic line ratings could affect. When it came to the worst case scenarios that I discussed, things like gusts, if the sensors don't work, if communication links are broken, we worked that out with PGM, who was also excellent to deal with related to this. And they actually put in things like smoothing algorithms on their end, where it would somewhat, add some conservatism to if there was gusts and just kind of smoothing out what the rating would look like instead of it being, all over the place. And so I think it's important to just put all of those things on the table and have a plan for each of those and reaching beyond the utility itself for partners on the regulatory front, the compliance front, RTO, and bordering utilities front to basically work through those things.
Great, thank you. Michael?
Yeah, I would echo that we did something similar for the NERC side for sure. One thing I would add is that a lot of these solutions we've been talking to and have deployed are cloud-based solutions. And so then when we're trying to do integrations and SIP standards, we have to make we're making some assumptions and trying to make sure we're doing everything the best way we can do it. And so we've met with our Midwest Reliability Organization, talked about our how we're protecting the data, how the data is integrated, how it's transferring, we're doing the best things we can do. But at some point there will be cloud-based specific SIP standards. And so if these solutions are on the cloud and not on premise, we'll have to make sure that they're all following that. The other thing I guess we'd say is we also engaged our system operators very early on, because they're the ones that are going to have to, at the end of the day, deal with these ratings. So they're going to get the calls, in our case from ISO, saying, hey, what's the rating on this line right now? And so they need training, they need to be comfortable with it, they need to know where to go. Integrating with our EMS system, that was one of our processes, and one of the steps during that integration was to make sure they knew where to look and what's going to happen. The other thing is that so once we've integrated some of these into our EMS system has some capabilities to sort of auto replace data and so if we get data, for example, if the whole system goes down for dynamic line ratings, our system automatically sees that, recognizes it, sees the bad data, and replaces it right now with our seasonal ratings, and at some point with AMI adjusted ratings. So we took some things sort of out of in this case, our vendors, and kind of went to our EMS and did our own safety net to make sure if something happens, we have appropriate ratings for what we should be doing.
Alex, Watkins?
Yeah, I guess my lesson learned from applying grid enhancing technologies may be a little bit philosophical. So we have two very different regions that we provide services in. We obviously have our primary RTO footprint in the Eastern Interconnect, although we recently expanded that into the Western Interconnect, where we've had long-term planning processes and predominantly have built transmission rather than applying some of these grid enhancing technologies. And now that the industry is changing and there's a lot of drivers to that, we see more and more the need to get more creative. You're going to have to apply different solutions to meet those needs. The other side of it is in the Western Interconnect, where we've been providing reliability coordination services since like 2019, recently expanded the RTO in the Western Interconnect. A lot of those utilities in that region, I'd say rather than investing in long-term infrastructure and building transmission lines, they've applied various grid enhancing technologies, whether it be phase shifters, topology optimization, remedial action schemes, some dynamic line rating things to prevent the investment, not only just defer it. That was their solution, and so our lesson learned now is with our RTO traditional Eastern footprint, we're maybe pointing at the West to say, like, see, some of these technologies do work. You can let go of some of your resistance to them. And in the West, we've said, like, oh, it wasn't your final solution. You do need to invest in infrastructure. So I think our lesson learned is seeing two very different approaches to it that have materialized over the last couple of decades. Is that neither of them maybe hit the sweet spot in it. And so there's a lot of benefit to applying these technologies. Fast implementations, you can fix congestion problems relatively quickly, but it's not the end-all, be-all solution. There is still a need for that long-term investment in infrastructure. So seeing the two different interconnects, apply them very, very differently, you see challenges with both, with the one side that was resistant to it and the other side that leaned heavily into it as a replacement.
And Alex, with your stakeholders, are you seeing, when you're presenting these arguments, are they receptive to what you're saying, or do you feel like there's still some hesitation that somehow could be addressed?
I think it would depend. It depends on what kind of thing that you're referring to. So, for instance, in the very short term, because you can implement it almost immediately, we currently have a project going with Idaho National Laboratories looking at topology optimization. You know, that's something, reconfiguring the system has always been around, but we would like to look at it from a broader perspective of not just like reliability. You know, in a lot of ways, reliability and economics are inseparable. So when you start, suggesting that you reconfigure the system to reduce congestion costs, a lot of our utilities are really hesitant to that. So we're working with those utilities to make them more comfortable. I think over the last year we've made a lot of ground on that front and showing that it can be done reliability and it provides net benefit. Some of them, I think they'll just have to see it work. For some of the other technologies, because it does require investment, people want to see the cost benefit of it. So, I can propose it just because it would be neat, but that doesn't really fly all the time.
Thank you. Andrew?
Thank you. So as we initially started deploying DLR, we were sort of doing it on a line-by-line basis. And we got sort of mixed results in terms of which lines we put it on. And, what we really learned was that it's sort of very weather-dependent, very geography, topology dependent. So you might think you're going to get 10% extra on, and it might turn out you get 0 or 1%, and others you get more than 10%. So really a big lesson learned is just how integrated the system actually is, and we believe we're going to find a lot of value in putting it up, sort of blanketing the system so we can really run the system optimally all the time. So I think that's a perspective that we've sort of changed as we've started to deploy this. Cyber, again, is a huge lesson learned, or just a concern that we've been addressing as we deal with it. And then something that we're still sort of feeling out is how much maintenance are we going to need with this equipment, right? It's different than a transformer, which sits there and you test it every once in a while. This sort of needs constant monitoring and a bit more governance around how you maintain it. Also, just to change a little bit of the subject, to the high performance conductors is another sort of advanced transmission technology that we've used, and what we found there is that it's very situationally dependent where you use those. So if you have a line that has asset condition issues and you can't reuse the poles, then you're going to be rebuilding the line anyway. So at that point, you're looking to potentially use advanced conductors to maybe respan and install less poles, but the topology may not allow for that. And in that case, the advanced conductors are not worth the cost. But in other cases, if you can actually reuse the line, or you can reuse the structures, or you can respan, then you do start seeing those benefits. So it actually, as you get into the physical design of the lines, there's a lot of different applications. So it sort of makes the engineer's job a little bit more complicated to figure out, are they using the right, the right conductor for the right application.
You just made me think of a follow-up. If the benefit isn't like primarily congestion relief on the advanced conductors, what is the benefit, I guess?
Yeah, so what we will usually see is we're trying to solve a specific problem, right? Maybe we're trying to upgrade a particular line. And in that case, we are essentially trying to address congestion, but the system as a whole is not congested, but occasionally you'll have, growth on the system from one thing or another that may require you to upgrade, a particular line. And at that point, you can use an advanced conductor, reuse the structures, and it's quick, easy to put that in and get that rating that you're looking for. But if you can't reuse the structures because maybe they're 100 years old, which is not uncommon in New England, then you see diminishing returns with that is kind of the point I was trying to make. Thank you.
Thank you. We'll do Michael and then Saugata.
Thanks. That's actually nice. I have a very quick comment. I just wanted to mention, I think Alex was talking about these DLRs and their deployment. And I think you mentioned at some point that DLRs kind of are looked at sort of a replacement potentially for some builds. And I guess that for Great River Energy, we're not really looking at it that way. We're not looking at DLR to replace upgrades and required upgrades. We're still doing we're still doing tons of build out. It's sort of another tool we have for congestion relief, or it could be a temporary relief situation where we have to build 1,000 miles, we can only build 200 miles this year. Well, then in the meantime, we could use things like DLR and other tools at our disposal. So I guess I'd say that a lot of places that we deploy DLR are also areas that we are considering for system upgrades, because if it already needs DLR for additional capacity and where there's causing congestions, at some point that'd probably be a good opportunity for us to upgrade that line anyway. So thanks.
Yeah, we are working with some of our transmission utility customers, and they are taking a very interesting approach here, which is kind of similar to what, Michael, you mentioned, because it's not about whether it is conventional network upgrades versus GETs. It's never that. It's not one of the above, it's all of the above. What can we do to accelerate the interconnection of projects? What can we do to reduce the cost for the ratepayers? And when we do that, what they are trying to do, and we are helping them with that, is can we look at it as a short-term solution and a long-term solution? GETs can be a good intermediate short-term solution that can actually increase the capacity where it is needed for the grid, get the projects in that are waiting in the queue, and while they are getting in, and they're also gradually going through a ramp, whether it is a load or generation, you are still parallelly increasing or building your new infrastructure. But what that is letting them do is it's not stalling the interconnection of the projects. So if we use GETs in combination with network upgrades, and we do both of them optimally, combine them properly, I think that's where a lot of our transmission utility customers are actually seeing value by having that all of the above kind of an approach. So just wanted to mention that.
Great, thank you. And then Alexandre?
So I'd like to echo a little bit what was said, and especially Andrew saying that we need to be thinking about GETs not only as individual projects, but more as in terms of using it across the system. And to illustrate this, I'd like to spend just a few minutes to talk about a relatively innovative solution coming out of Europe, which is something that's called NASA. It's a zonal automaton. That has been developed by RTE, the French transmission system operator. And in a nutshell, what this does is it looks at a pocket of about 10 transmission lines, usually in a wind-rich area, and monitors the system in real time, knowing that there can be congestions if, for example, there is a lot of wind, or and so you can optimally build the system to handle to have some level of this congestion, which you can alleviate by remedial actions such as doing limitation on the wind. But of course, you'd like to limit that as much as possible. So this automaton looks at this area in real time and determine among all the different solutions, which can be available capacity from DLR, which can be error configuration, which can be any kind of limitation, what is, in that present state, optimizing your system, the least cost way to lift the constraints. And so it does two things. Essentially provides an optimization of that thing, and it basically waits for the last time to make this decision. And so this is one interesting way of looking at how you operationalize DLRs or topology optimization by having these very rapid layers that acts typically in the order of seconds. This is something that no operator can actually react this. It would do what the operator does, but it does it in a much faster way. And so that allows you essentially to lift the constraints. So this system is not theoretical. It's been deployed in France in about 20 areas. And so in this area, the planning studies would say that typically you would have, on average, 50, 60 hours of limitations of your wind power. By exploiting this capability across this zone, you essentially limit that time to 0. And this system is actually operational, it's been used. That means this system fired sometimes and automatically does these constraints. So to me, lesson learned is essentially, in order to do that, you need to have a pretty good access to your system. So this was possible because in France that was done directly by other system operators. So we didn't have any problem accessing CIDs, for example, that was directly there. I haven't checked in detail, but I think that the system would probably be uncompliant with with many of the NERC guidelines. So that means that you would need some kind. This shows that you need some kind of leeway to implement these kind of things. And the last thing, it works because it's not a black box system. So the utility really knows what's inside there, and so you are able to manage the risk that is associated with this automatic system. It's not a remedial action scheme, because a remedial action scheme, which you may be familiar with, is just if then else. It's just a very deterministic here. Here it really runs an optimization in real times and determine these kind of things. So I just wanted to highlight a little bit of this innovation, because it shows the realm of possibility when we do use software efficiently on top of GETS. This is where you really get the most out of the system.
I think you were describing the entire country almost as like one zone for this.
So in this case, those zones are about 10 substations, and they're mostly used on the sub-transmission. Because part of the reason is if you use it on a very large scale, then the optimization becomes too complicated right now. There's a lot more variables, and basically, so it's 20 zones. And right now, actually, one concern is that it's actually growing. There's the question of, okay, each zone functions correctly, but when you put them together, are there going to be interactions? So we're having actually a lot. We're seeing in France a lot of research on actually dealing with.
I guess where I was going is, what would be the most analogous zone in the United States? A utility, an RTO? Would that be too wide?
I think a utility would be far too wide. It's really like a sub-transmission pocket. Think about a TED substation, perhaps a few counties, I guess, a county, right?
Thank you.
Emilie?
So I have a couple of learnings to share, but do want to comment quickly on NERC SIP compliance. One trend that we've seen with our customers is, I mentioned CEII security before, a shift towards more on-premise deployments. So we have designed our software and our platform in a way to accommodate that. I'd say we have a range of being fully on cloud. We have some customers where we basically containerized the line ratings engine. So this, secure area where those critical ratings are being generated is fully on-prem with connections to our weather service and other critical services. And then we also have a deployment that we're working on in Europe that is a fully on-premise appliance where the only connection to the outside world is weather data. And so I just want to highlight that as kind of every utility security posture is a little bit different. It's evolving quickly. You mentioned there potentially being NERC-CIP standards for cloud, but in the interim, there is a need to act, I think, on utilities' behalf to figure out how to be secure and not put that data at risk. So a couple of things we've learned specific to DLR. We started off at LineVision as a very sensor-forward solution. Over time, both with the sensor data that we have available to us through our deployments and some advances we've made in using computational fluid dynamics to downscale weather forecasts, we've seen that even going from publicly available weather services to that CFD downscaling, we can see a 54% improvement in wind accuracy forecasts. So that has really unlocked for us the ability to look at, as Andrew mentioned, the entire network in a cost-effective way, and then using the sensors really to address critical areas where there is high congestion, where there's sheltering, for example, on a line due to vegetation or topology. We also use the sensors as a source of calibration. We're all becoming familiar with AI hallucinations. Those sensors in the field allow us to have a ground truth and ensure that we are maintaining accuracy and precision over time within our models. So we found that that's a really a better approach, both from an accuracy. I've heard Michael say in the past, we need to know if the DLR is right. Like, is it accurate? Do we feel that it is up to the standards of all of the other data that's in the system? So the sensors help us do that. There's also kind of a tertiary benefit, I'd say, around capitalization. So being able to move DLR and these types of deployments into the capital budget versus the operational budget has some benefits for utilities, just in terms of being able to deploy. So having physical hardware is a lot easier to capitalize than software. One other thing I want to highlight is DLR is not always a happy capacity story. We have found, depending on the static wind assumptions or even AAR assumptions, that sometimes we are showing negative capacity. And in some cases, that can be really challenging for utilities because they're basically saying, I'm already constrained, and now you're telling me that it's worse. What do I even do with this information? Do I even want this information? It's a really challenging position to be in. But we have seen a number of utilities say, we want this information from a reliability and resilience standpoint. We need this information, and we will figure out how to adjust to it. So we have seen, some, Andrew mentioned, there are some lines where, there's maybe only a 1 or 2% uplift, or maybe there's no uplift depending on the season. But that is still grid intelligence that is useful for decision making, upgrade, justification, things of that nature. So just want to call out that sometimes it's not just that capacity story.
Yeah, that's a really great point. Michael, and then Saugata.
Yeah, that's actually the point I was going to make, is that it's not really for us like a magic bullet. And I guess, we're deploying DLRs and we're seeing success. We're deploying with 2 different vendors. So when we're really embracing it, we're really doing it. But the benefit you get is going to be based on your assumptions for your seasonal ratings. So the more conservative you are with your assumptions, the more benefit you're going to get when you get the dynamic line ratings. I think we should start calling them actual line ratings. I think dynamic line ratings in the industry has this connotation that you're going to magically get all this capacity. That's not always true. A lot of times you do get additional capacity. And a lot of times for us specifically in Minnesota, we need additional capacity when the wind is blowing, where we have wind farms. And when the wind is blowing is when the line is cooled, which is when we get the most capacity. So we have a really good correlation between when the wind farms are trying to cause congestion when we actually get additional cooling. But just to put a number to it, for us, about 5% of the time, I think we see less capacity than our seasonal. And we have more conservative ratings than average, I would say. So I would say people that have more aggressive ratings probably are going to see maybe less than that. But again, sometimes there are a lot of factors. Sometimes it could be right when you need it, but there are times we have less capacity. And our feeling is you have to accept that all the time. These are actual line ratings. You can't take only the good. So it's good or bad. You have to figure out how to operate to those ratings. But thanks.
I agree with Michael here, because one of the observations that we have had, again, with some of our ISO partners and transmission utilities with respect to dynamic line rating, is the very fact that the name says dynamic means it's changing. And it actually depends on multiple different factors. Wind speed and wind direction with respect to the line conductor is a massive factor that finally decides how are we looking at the rating, whether it is a positive gain or whether it is a negative gain as well. And we have seen both with examples that we have. And one of the key things here is, again, when it comes to DLR, one of the things that we think is important is it is important to have a wide area of visibility of all our transmission lines with DLR. And one of the ways to do that is actually having sensor-less software-based DLRs complement the sensor-based hardware DLRs. And that way, if we can scale across, we can actually think of one as the backup of the other, because that's one of the discussions that came up. The second thing is the DLR right? I mean, the odds of two different technologies giving wrong values and exactly same values, that is pretty low. So that is one way of validation as well. And one of the interesting observations that we have had with our sensor-less DLR software, working with two different ISO footprints, was about the critical spans that I wanted to bring up here. As we know that a particular transmission line has multiple different spans, and what finally dictates the rating of that line is one of those spans that is the critical span that limits the rating of the entire line. So it may be a 50-mile long line, and there is one span that is actually not getting cooled like the rest of the line, and then that becomes the limiting factor, and it derates the line. Now, if we actually have a digital twin kind of an approach with a software that models the entire line and has spatial and temporal redundancies in which we build that digital twin model, which is what we do at GridAstra, by the way, and then add the computational fluid dynamics on top of that, I think that is one way that we have seen that you can actually have a good visibility of the entire stretch of the line and find out these critical spans. I'll give you an example. There was a line that was 2 miles long, actually to be very precise, 2.2 miles long. And each span of that line over a course of just 3 months became a critical span. So even if it is a short line, it can have multiple different spans becoming the limiting element. So it really doesn't matter. We have had lines that are more than 50 miles long line. Each span of that line at some point of the other during a 3-month time became a critical span. I think that's one of the reasons that we also think that can we complement the sensor-less software DLR with the hardware sensor-based DLRs, and both working together can actually get the biggest benefit, whether it is about finding the true ratings that you mentioned, because if we overestimate the ratings and miss out on these critical spans, that's a reliability risk. On the other hand, if we are not extracting the complete juice out of the existing infrastructure, we are losing out, and that creates the congestion cost to go up. So I think a combined approach is what we have seen with our ISO partners that could be one of the ways forward. Just wanted to add that.
And just to follow up, I know that there's some concerns when we have like risk appetite when we talk about this. So do you think that helps alleviate some of the risk adverse stakeholders and their willingness to want to adopt when you talk about it?
Absolutely, because one serves as the backup of the other and kind of complements, and you can see the ratings. And we can have multiple different ways in which we can present those values, but that definitely is helping, which is the reason we started working with some of the ISO partners on this.
Great, thank you, and I'll give it back to Jesse for our next question.
Before turning to Jesse, I want to follow up on a couple things, and I think the question's for Michael and David, but it might end up being for Alex. Michael and David, you both described the challenges of deployment with the RTOs you work with in terms of working with them closely to get them comfortable with primarily with DLRs and learning together how best to do that. Similarly, you described working with NERC to get them comfortable with that. And so it sounds like you've developed that for Great River and PPL within the RTO and within NERC do you see that they have, NERC and the RTO has taken those lessons and applied them to other utilities? I'm a little concerned I'm asking you to describe other utilities' experience, which was why the question may be for Alex. Have you been able to kind of scale some of the lessons learned from working with the utilities? So I'll start with Michael and David, and then give Alex some time to think about that.
Sure. Yeah. So I guess on the maybe the NERC side of it first, there are other utilities in Minnesota that are doing also dynamic line ratings. And so when we met with the Midwest Reliability Organization, we described what we're doing. We told them a path. We walked them through our integration path. We told them all of our sort of security checkpoints and everything we did to try to protect the data to every way we possibly could, the way it is today. And we talked to them about it. They said they didn't have any red flags. It wasn't an audit. It was a voluntary. We went to them and said, hey, this is what we're doing. What do you think? So this is more conversational. But they didn't have any red flags at the time. I don't know, to your point, I don't know if I can speak to their utilities, but I have talked to them about what we're doing, and I've kind of heard about what they're doing, and I think we're all taking similar approaches right now for everything we can do when it comes to cloud-based technology to try to protect it the best we can. I think we are maybe not worried, but curious and perhaps concerned when the rules come out for cloud-based software that we can meet them all. There are some things too that at some point you have to look at what's a SIP asset and what can be in the cloud and what can't be in the cloud too. And so I think to your point too, at some point we can do on-premise. Even for the on-premise, at some point there's going to probably be some data coming from the external world into feeding that system. So is it weather data? Is it the line rating? Is it somewhere along the way? At some point you need an external data source to probably get these things working. So at some point we're going to have to find a good rule to sort of allow that to happen, I guess. For MISO, they have, as they've been building out their ambient adjusted rating program, they have places where you can configure ratings, any sort of dynamic line ratings, whether it's ambient adjusted ratings or dynamic line ratings or seasonal or whatnot. So with them, we work with them for what we're doing. We communicated, made sure they're using the ratings, but the actual integration part is sort of part of their natural process, which is really good. We didn't have to do something above and beyond or separate necessarily for dynamic line ratings for the real-time ratings. For the day-ahead ratings, we're not sharing those with MISO yet, which would be where we're getting arguably more benefits if we were in the day-ahead market for those ratings. And MISO's still, as far as I'm aware, developing that capability. So.
Yeah, I think I'd say so. On the compliance side, reliability first and NERC, from our observation, once we worked with them and it seemed like they had discussions with other utilities also, they were very transparent to, I'll say, the community of the way to navigate the NERC compliance standards as you continue to install dynamic line ratings. So I actually feel like they did a great job facilitating and laying out that groundwork for I'll say, all of us. When it comes to working with the R2 and PJM and getting others plugged into the day-ahead market and accounted for in like transmission windows and things like that, it is hard to speak on other utilities. But I think what I would say, though, is from our perspective, almost all of the work that we did with PJM to iron out the things like the smoothing algorithms, Michael, he raised the point of, you could lift the rating of the conductor, but you might have a limiting component of the substation. So you almost have to have like a temporary ceiling until you alleviate that limiting component. So some of those moving parts, what that process looked like, as well as the API between our operational system and PJM so that the ratings were sent over every 5 minutes. That all, from our perspective, is pretty much general. So it kind of could be a tip of the spear for anyone to leverage that. We know of other peers that have sensors in the air or their lines. I honestly don't know how those are plugged into the market or not. But what I will say is, for us, when the first 2 lines that we put them on, and to give the specific, it was Harwood, Susquehanna, and Juniata, Cumberland. We put them all those lines because they were showing congestion in an upcoming competitive window. So we wanted to see if dynamic line ratings could eliminate the need for a project. One of them it did, one of them it did not. Since then, we do that same process. So if we see that there's congestion coming up on a line, we'll put sensors on the line, we'll see if dynamic line ratings alleviate that. But whether it does or doesn't, PJM immediately plugs them into the market. So it just shows that now that it has been done, it's relatively easy to replicate.
So we have one of, if not our biggest utility within our RTO footprint, does use dynamic line ratings, and they use it almost across their entire system. I don't know if they have it on every line within SPP, but it's definitely the vast majority of them. And we went through all the growing pains of like, it was probably early on in my shift days of like you would see something load up and you had to actually call the utility and ask them what it was. But since then we've integrated it. We receive all that over ICCP, integrated into our EMS systems, and all of that infrastructure is available to all of our members. So if we have if a different utility wants to implement DLRs, we're ready to receive it today. Largely, I'd say we haven't seen a huge appetite from most of our more risk-adverse utilities for a variety of reasons. I will say that our implementation of AARs with our limit exchange portal, I think makes that data exchange a little bit more robust because you are applying it, into a 10-day forecast. It can be applied to the day-ahead market. You can set boundaries on, for if you are like substation limited, for instance. So you can take that ambient adjusted rate up to a point, but then you have some other facility that limits how far it can go and things like that. So obviously, I think that'll be a stepping stone for people to go more towards dynamic line ratings once they fully integrate their AAR approach and work through our limit exchange portal, have access to their neighbors. They can be applied, full day ahead market integration with some safety boundaries and things like that. I think will make people more comfortable with it. But overall, a lot of the utilities, for all the reasons mentioned, like, it's more complexity, it's harder on our operators, it's maybe your masking congestion costs, like all the things have limited people's interest in applying it. But our utilities that have done it successfully, and we've kind of worked through the bugs to get it fully integrated with our EMS system, and it works.
Thank you all.
All right, my next question is actually a softball. You can do it by show of hands. Did anyone else stay up too late yelling at the U.S. men's national team defense? All right. Yeah, definitely. So with that in mind, I'm going to ask one more actually on-topic question, and then we'll take a short break, like 10, 15 minutes. Sometimes we use GETs as almost synonymous with DLRs, AARs, but the reality is there's a whole lot of technologies out there. I can think of at least 5, probably more than that. So the question is just, which GETs do you think are easiest to deploy in terms of time, maybe money, software integration, anything else that makes the deployment happen sooner? I saw David Quier first.
Excuse me. For speed of integration, all of the GETs, for the most part, by nature, are fast. At least from our view on that. Advanced conductors might follow a typical infrastructure type path, but for most of the other technologies, they're relatively quick. So for us, it comes down to benefit to cost. So we tend to gravitate to dynamic line ratings because when you do benefit to cost ratio on dynamic line ratings, alleviating congestion, it blows everything else out of the water. I mean, it's inexpensive technology for what it can defer or eliminate. When we've gone through our benefit to cost ratio on some of the other techs from a PPL perspective, I just speak for us, we look at it for the total life of the asset and the customer, to the customer compared to the alternatives. So if we're going to build a transmission line to a 60 or 70 year life, and dynamic line ratings can alleviate congestion to eliminate that, or et cetera, it tends to be a check mark. Some of the other technologies might have shorter lifespans, 20 years or less, maybe higher maintenance, and then you start to extrapolate it along that time frame, and it starts to, the benefit to cost ratio doesn't always seem to be as good. And so we always stand ready to evaluate all of the different technologies. Just one of the things we've pushed back for the GETS vendors is just to look at it from that same lens. Like upfront cost is one thing, total cost over the life of the asset is another, and we would love for all of them to pass that bar, but from our perspective, not all of them do.
I saw Emilie next, and then Alex.
So I obviously have a bias around DLR, but I'll echo some of what David said around speed to deployment. I mean, where we sit right now as LineVision, we could actually deploy DLR across the entire country right now using publicly available data. Obviously, to have more accurate ratings, we want to have utility source data so that we are improving the fidelity of that accuracy, but it's very quick to deploy with the way we've built our infrastructure. One thing that I'll say from a GETS stacking standpoint, having DLR, the ability to understand both historically and from a forecast perspective what the ratings of a system could be, it's useful for planning and operational use cases, but having that power flow component is also extremely useful. So identifying a massive capacity uplift on a line that is not utilized or is 40% utilized is not really telling the whole story. That's where we do see more of a challenge from a speed of deployment perspective. That's very sensitive data. Again, drives back towards that on-premise conversation of, how can this data be used in a secure way? Probably going to be on-prem, and that's where we see more of the delay.
Alex, please.
I mean, as far as things that can be quickly deployed, I think there's a couple. I mean, obviously there's topology optimization and remedial action schemes that I think are maybe underutilized. A lot of utilities that we have that are resistant to them, they have legitimate concerns with just, maybe the system wasn't planned that way or whatever it may be, but there's a lot of benefit in those for, like, if you already have identified a need and you have a long-term capital project being built, but it's going to take 6-8 years to get the steel in the ground, those are things that, I mean, a topology optimization can be implemented today, if we can get everybody to agree to it. You just have to have the correct modeling in place to study it both real time, to understand the transient and stability impacts of it, and apply it to your planning models moving forward. Some of those, when we do transmission planning, you do kind of system intact, apply future load forecast, and plan the system. Well, in reality, the transmission system, we may have hundreds of lines out of service across our footprint on any given day with just planned transmission work. So it's a very dynamic thing where, if you have this known transmission outage that's going to be out for 6 months, maybe you can implement a short-term remedial action scheme to mitigate a concern to keep a generating resource online during that outage or whatever it may be. Or, if you have planned work and you stack forced outages on top of it, there may be things where stuff just pops up and a topology optimization relieves stranded capacity. So those, if you have the study processes and the real-time situational awareness stuff in place, those are things that can be implemented almost immediately. I mean, topology optimization literally can be implemented in minutes if you can assess it and make sure it doesn't create a new concern.
Yeah, let's go down the line. Andrew and then Alexander.
Yeah, thank you. It was a simple question, but it's really actually a tricky question, because the answer is it depends, right? All these technologies are solving different problems. So I think, something that's sort of software based, like, a DLR, or, can be really quick to deploy, but it might not solve the actual problem you're trying to solve for, right? So, if you're trying to get more renewables online quicker, you need something, like a synchronous condenser that might be a little bit more capital, but it's a lot quicker than, say, a new power plant, right? So all of these are, like, for the applications that you're trying to use, they probably are the quickest way to get there, and they may be a temporary sort of bridge solution, and it might be best to think of them from that perspective. But I think they really are all solving for different problems. So I don't think you can say what's the quickest. It depends on what you're trying to solve for.
So I'll echo some of Alex's comments on the topology optimization. So again, in Europe, as you probably know, the transmission system operators have the double hat of system operators and a transmission owner. So basically, in this situation, the transmission optimization is just a purely internal company discussion, and in that case, basically, many of the barriers that you encounter here in some discussion between the RTO and the transmission owners are completely evaluated. So transmission optimization is used pretty much across the board and to great effect in there. So you can deploy it very fast. I'll echo towards the things is we had a lot of discussions about DLR, but as it was pointed out, actually thermal limits are not always what you should worry about. I think voltage stability and small signal stability are also increasingly determining some of the limitation we have in the system, and in some cases actually they can introduce pretty big reliability risk. If you look at the Iberian blackout report that was issued this year from this and do a simple search about DLR, there's no mention whatsoever of this because it was basically a voltage management issue. And I think I would, and perhaps you can tell me if that's the case, but I see a lot of system operators starting to struggle managing voltage within the bonds and doing your stability limits with gates to other kind of gates that we've not talked about too much, like your StatCom, for example. And so again, it's not like there is one. It's exactly what you said. It's not like there is just. It's not the speed of your deployment. It's what it addresses as needs. I think in terms of speed of your deployment, the main thing, and we've talked about this already, is your software system, your software environment, your planning tools, your EMS needs to be get ready, so that basically the get is just plug and play, and it enables to do things like if you need it for a very short duration, like even a planned outage for a couple of weeks, because that's the best way to actually manage it on an economical point of view. Your software should not be the implementation about deploying it. And we are sort of getting there, but we are pretty far from it. And again, I think that open architectures could actually be very helpful in making that possible.
We'll keep it going, Saugata, and then we'll finish with Michael.
Yeah, in general, GET's deployment is pretty quick as compared to the other alternatives that we have from a conventional kind of network upgrades perspective. One of the things I wanted to mention here is, like, even within GETs, like, of course, there are different types of GETs as we know. Even within that, like things like topology optimization, that's completely a software problem. As long as we know which are those like transmission lines or buses in the substations that have circuit breakers that are, for example, SCADA controlled, that can be controlled in real time really quickly, then it's essentially a software problem that we are dealing with. It's a software optimization problem of the grid that we are looking at. Pretty easy, pretty quick to deploy. But we have to plan for that, again, in the planning as well. So planning and the operations would need to go hand in hand to be able to replicate that. Like, for example, can we start thinking about the topology optimization even as a kind of a remedial action scheme? Because at the end of the day, you are taking an action by doing a switching action based on a certain condition under a given contingency. So, I mean, I typically say this, like when we talk about flexibility of the grid essentially starts with flexibility of the mindset that we have. Are we willing to change the ways in which we have planned and operated earlier and get into a new kind of a mindset of planning the grid of the future and operating the grid of the future likewise, right? So that is where topology optimization can be really, really handy and can be really quick. Even if we plan the power flow controllers, during the planning, having the power flow controllers actually reroute the flow of power in real time during operations can actually be done pretty quickly. So these are things, again, where software plays a significant role in telling that, okay, how do you reroute power without causing any other reliability issues during your operations? And one other important thing is typically when we do the planning, especially the long-term transmission planning or even interconnection planning, we are typically dealing with the boundary cases. So in boundary case-based assessment, you can only look at certain handful possibilities even when you are planning the grid. And that is where it becomes absolutely important to have this similar kind of a replicability of a software in operations as well, so that if the conditions are different from what you had planned for, you can still quickly adapt to the real-time conditions and have the software provide the decision support mechanism with the different types of gets that you have already had in the grid. So I think at the end of the day, these are all quick. It is just a mindset shift that may be needed.
All right. I really like grid enhancing technologies, but I might bring the room down a little bit here. I guess I'll start. So for software-based, I agree. Software can be very fast. We've talked to vendors that within a day could do our system and show us ambient-adjusted dynamic line ratings, multiple vendors. The question always with that is going to be you have to do something with that data. You still have to integrate it. And so, for example, and also that's true for a lot of the hardware ones too. At some point, you have to get the data somewhere else. So it can take a day to get the system set up, but from our point of view, our Great Rivers, I mean, you still have to integrate it, you still have to protect it, you still have all the concerns we've talked about earlier for cyber and that sort of stuff. And I guess an example I think about is ambient adjusted ratings. That's purely software. And a lot of the ISOs have asked for extensions. We're not fully online yet. So even though it's just software, it can be very complex when there's a lot of moving parts. And when you're talking about even software-based implementations, a lot of times you need transmission information. So you have to have, it takes a little bit more. There's more steps and more stakeholders than maybe it seems like up front, even though you could get the data immediately. I could get the data today, but until I couldn't do something with it today, I guess is what I'm saying. We've done software-based stuff. We've done hardware. So for dynamic line ratings, for example, we work with Heimdall. They use drones to install and energize lines. And so for them, for our first pilot project, probably less than 6 months from when we talked to them to when we installed that on our line. So within 6 months, we had that on our line getting data. It took longer than that to integrate back to our EMS system and with MISO and do the rest of the build out. But to install something, a hardware type solution, that was pretty quick. And I think in our experience, the grid enhancing technology companies are very happy and eager to work with you and try to get these things installed. I think as we mentioned, advanced conductors, StatComs, we have both of those. Those kind of follow typical transmission projects. Those are going to take a little bit longer. Things like topology optimization, I agree, same thing. We could do it probably today. There's a lot of other considerations when you start doing that. If you start opening breakers, and there's things like breaker maintenance, and switch maintenance, and there's more things, I guess, to consider typically around the grid enhancing technology software platforms than just the software itself. I think the software is actually the easiest part, honestly, to deploy these. The hardest part is integrating it and then making sure the rest of the system works with it. You're working with your neighbors, your ISOs, your maintenance is up to date, all your systems, your checks, your FAC, things are all up to date. So it's actually, in my opinion, very easy generally to put these out there. The harder part is getting it where you can operationalize it and actually use it and have everything else at your system at your utility ready to go. So, yeah. Oh, actually, sorry, can I add one more thing?
Yeah, please.
Sorry, one more note that I had. So we use Heimdall for dynamic line ratings. We also use Prisma Photonics, which uses the optical ground wire as a sensor. So it's distributed acoustic sensing. And that was also very easy to install because that was like half a day you install it in the substation as long as you already have fiber up. And so there's some of these things where, like that one, for example, if you already have OPGW, which is the shield wire, the optical shield wire, you can install that in half a day. But if not, it's same thing. It's a typical transmission project to sort of install the fiber. And then also, once you have that data, you still have to integrate it back in. So it's, I guess, more of the same story, I'd say.
Yeah, thanks. I think earlier I somewhat inartfully asked, about who owns the data of Alexandre, but I think in reality it's like, what's the chain of custody of that data? Because even if you're taking publicly available data, in my mind, once you transform it, it might become proprietary, and then where does it go? But you can noodle on that. I think it's 10:44 by my iPhone software. Let's reconvene at 11. Thanks.
Just some time.
We'll get going again. Maybe? Hey, I don't have a gavel. All right, welcome back. So we're going to go for about an hour and a half-ish, and then we'll break for lunch. The next question, though, I'm going to turn it over to Stefania.
Yeah, welcome back. We've loved the conversation so far. It's been really illuminating. I kind of want to turn back to a point that Saugata had brought up earlier. So how are new software platforms such as real-time analytics or digital twins changing the way that system operators identify and make use of latent grid capacity? And we can start out with Saugata.
Thank you. Yeah, actually, this is like probably a little bit of a continuation of the first comment that I made earlier this morning. I think the way we see it is software is going to play a massive role in actually even in the deployment of the GETs. Because when we talk about GETs, again, it's like, I know we are talking a lot about the DLR piece today, but like, as we know that there are multiple different types of GETs, topology optimization being one, power flow controllers, even advanced reconductoring and others, right? And the point is, when we are trying to plan for the grid of the future, whether it is for the interconnection, fast tracking of the interconnection, or even for the regular transmission planning, the long-term transmission planning, we need to know, for example, we need to have different options that, okay, what are the different types of GETs that actually would add value in a certain situation? How can the GETs be combined with other type of network upgrades that are happening? So it's a co-optimization of not only across different types of GETs, but also co-optimization of the different types of GETs with the conventional network upgrades, because you have to look at the whole picture. It's not going to be like a piecemeal kind of a view that we need to take. We need to take a broader view of the system planning, and we need to make sure that like it's always reliability first, and we do not affect the cost payers or the rate payers when it comes to their electricity costs. So, and when we do that, again, it's the permutation combinations are massive. You can actually solve a reliability kind of problem in multiple different ways. And what are those different ways? What would be the cost for each of those options? Which GETs make sense where and why? Having a data-driven decision-making ability is, I think, of paramount importance here, which is where the software starts giving you a head start that, okay, here's the problem, here's the different types of solutions that we have, here's the cost of the different solutions, here's the timeline of the different solutions, and even things like if we dive down a little bit deeper, for example, let's say power flow controllers, right? There can be different types of power flow controllers. Now, where do you optimally place those power flow controllers so that with the least amount of power flow controller deployment, you get the maximum benefits? And how does that work together with the other type of either GETs or the conventional network upgrades? So from a technical perspective, the computations are massive, and it's like the scale at which it needs to be done, and if it has to be done repetitively, and if there has to be a solid technical defense mechanism to say that, okay, this is the reason why we did this, that is where software becomes very important. And that's where we are seeing multiple utilities are actually opening up for that, and which is great news. And they are actually using software now to make those kind of decisions.
Just a follow-up, I think maybe it was Andrew earlier talked about the deployment costs and how you measure them. Is it just the upfront costs, or is it like the lifetime cost of the system?
It is
How do you
both.
recommend?
It is both the capex and the lifetime costs that we would be able to evaluate for any type of GETs and compare that with that, okay, if this kind of whether it's an interconnection planning needs network upgrades, the conventional type, here's the cost, versus if it were to be done with GETS, here's the cost, versus if it were to be done with a combination of GETS and network upgrades, here's the cost. And it would be both CapEx and over the lifetime kind of cost comparison. And we are able to do that today already with the software.
Go to Alexandre.
So yes, absolutely. I mean, I absolutely agree on the computational requirements. I just want to point out that it's not in the realm of impossibility. So every 2 years, ENSOE in Europe, again, sorry, I'm bringing Europe a lot, but I think there's a lot of inspiration here. ENSOE does a study across the entire European network, which is called the 10-year network development plan. It's the historical name because the planning horizon is tending to be more like 20, 25 years now. So it's changing, and it's a planning study. It's coordinating planning studies by all of the operators across the entire European footprint in order to identify essentially projects or opportunities to enhance cross-border exchanges. So as you know, again, Europe function on a zonal market. If you think about it, every zone is about a country. There's some countries that are split and everything, and Europe has this mechanism where if you identify a situation where a congestion constraint or any kind of constraints, can be voltage stability or anything, prevents this exchange in a way that disoptimizes the system too much, you can propose a project which can be a regular project or a GET project, and if the cost-benefit analysis says that this is positive for the system, then you get actually pretty good. You get identified as a project of a common interest, and the European Commission puts money on the table to facilitate the project. So it's a little bit of a different construct, but what that means is those studies are done under the entire footprint of Europe every 2 years with a very well documented cost-benefit analysis methodology that's available for everybody to do. It has its own stakeholder process, and in which GETS, actually, if you read through, GETS are explicitly stated as something that you need to study as an alternative for every kind of constraint that is not. I could read it to you, but essentially you can trust me. And so these studies are actually possible. What you need is you need to set it up, and you need the methodology, and then it comes down, as you said, this is a massive project. So there are a lot of improvement. There is a lot of research actually on doing this even more effectively, going to more scenarios. But it can be done, and it can be done in a way that identifies those GETs. And by the way, these frameworks tends to be used at a European level, but these methodologies are used on a country-to-country basis for their own transmission need, and they too use the same methodology in terms of cost-benefit analysis to determine whether a specific GETs or natural or a regular upgrade or a combination of both is actually the best way to deal with this. So it's a source of inspiration. Of course, I'm not saying this could be applied to the US directly, but it's possible, and those documents can be used as a source of inspiration to actually tackle this kind of thing.
Great, thank you. And then could we go to David, and then Emilie, and then Michael?
The question included the subject of real-time analytics, and we've been talking about the dynamic line ratings, and I know for us, every 5 minutes from those lines that have DLR, we get a new rating. But a lot of the benefits are unlocked specifically when it comes to market congestion pricing from the forecasting part of it. And so it's important that when you're entering in to deploying these technologies, that we're using real-time analytics, machine learning algorithms to hone our forecasts, because that's how it can play in the day ahead market. And then when it comes to basically being principled within our own companies, if you're getting a rating every 5 minutes, you're not depending on an operator to do something based off of new data every 5 minutes. So you're doubling down on automation type principles, more integrations like we talked about earlier. It's key that you have vendor software that plays nice with your EMS software that you're running your transmission based system based off of. And then even even just culturally, you can never have it within your company that one hand doesn't know what the other's doing. So ops, planning, and IT all need to be in lockstep, because you can't have it that dynamic line ratings, for instance, is on a line giving new ratings, but then when a planner and maybe another building somewhere is planning out something on that line, that they make a decision on what kind of substation equipment is there that now affects what that lighting would be. Everything needs to be in step with each other. But once you have that in place, then you just continue to, the benefits just continue to come. So that real-time analytics, it drives more automation, the need for more integration, and just the groups culturally need to be more aligned.
So when I think about latent capacity, I kind of think about two different time scales. So from an operational standpoint, you are looking at day ahead, you're looking sub 24 hours. For DLR, the most determinant variable is wind, and we all have experienced the excitement of poor forecasts that are longer term, even 10-day, 5-day. So from an operational standpoint, people are looking at the near term forecast, and that's where the most accuracy is, and that's where decision making occurs. What we feel we've unlocked with software is moving more on the planning horizon, where you're looking at a year out, even long-term 10-year forecast planning. We've built out the capabilities to have a 5-year look back on DLR across an entire network, and being able to say, these are the trends, these are the seasonal trends, here's what would have happened on your peak day in July when there was an ISO congestion issue. So what we have seen practically and how that can be used is having that look back and being able to say, okay, I'm interested in a maintenance window on this particular line or in this area. Being able to say, we believe based on our data, based on historical weather, you would be able to extend that window, say from just October into November. And so you went from a 4-week to an 8-week window. Then you have that operational data where you're looking forward and you kind of marry the two and say, yes, the wind is doing what we expect, or no, it's not, let's make a different decision. And it starts to affect that ability to see capacity and kind of marry the time scales in an effective and safe way.
I guess, is the utility rolling that in, or is it the grid operator? Like, who is using that look back, and how is it changing their behavior?
It's definitely, I would say, early days on how it's being integrated into the utility. That's mostly where we've been focused. So it is more, within the utility. I would say from a behavior change standpoint, it's, getting to the FERC order of using DLR and GETS in a 20-year planning horizon. This is starting to give them the tools to make that possible.
Thanks. If I could say what David said again, because basically I agree with all of that. But I would say for sure, automation is the key, because if you think about AMI-adjusted ratings, just as an example, we have about 3,000 data points, and we're not a huge utility, but we have about 3,000 data points traveling every 4 seconds, and an operator's not looking at that. They can't look at that. That's not just possible. So when you get to DLR, it can be a lot of data. You start throwing in all these different type of GET solutions. It's going to be hard for them to be constantly monitoring it, because generally operators are kind of reactive. They're waiting for something to happen and then they take action. I kind of think about our contingency analysis, which runs on the system to look for any sort of voltage contingencies or issues potentially. That runs every certain amount of time, every 30 minutes, 5 minutes, whatever. It pops up. If there's an issue, they do something about it. So from the operational point of view, they're not probably configuring this stuff. They're not necessarily setting up, but they need to know how to react to it, but only if there's something to react to. And operators already have so much on their plate, and so the more we can operate it or automate it, the better off we're going to be. I'd also say the planning side, the better you plan for these types of things, the easier everything's going to be after the fact. So, in our experience with our first dynamic line ratings, we kind of went a little gung-ho with it, got it up there, and we have it, and said, okay, now what do we do with it? And we had to almost take a step back and then look at where we should integrate it, what we should do with it. So, but otherwise I echo everything David said.
Great, thank you. I have a follow-up question for most of the group. I wanted to understand the current ability of the software to manage these technologies. It sounds like it's in development in some ways. It's further along on some technologies, like with DLR. But I wanted to get a sense of what that looks like right now once these technologies are deployed. how is the what kind of software do we have that can manage it? Go to Saugata. Thank you.
Yeah. So, the good news is we already have the software that can actually do all the stuff that I was mentioning. Like with GridAstra software, we can actually do these different types of optimization of the grid for the interconnection planning as well as for the transmission planning. And we have transmission utility customers who are already doing that with our software. So that is actually happening, and that's for different types of, and it's happening in different ISO footprints and different types of load interconnection levels that are coming up, or generation interconnection, or in general transmission planning. It's already there. So that's the good news that I want to share. And one other important thing is, it's again, like I mentioned, it's probably not just important to have this in planning. We should be able to replicate that in the operations, because conventionally the grid was not planned this kind of optimistically. And now when the grid is starting to get planned optimistically, then we have to be able to replicate that in operations, because we will start seeing new scenarios in operations, because we have planned the grid assuming certain things with gets. And once you make that assumption of gets in planning, gets the same kind of replicability of each of the different type of gets, whether it is DLR, whether it is topology optimization, whether it is power flow controller, or using the advanced conductors as reliably and as safely as possible, has to be replicated in the operation. So that's also coming along. So it has to be the same set of algorithms that have to do the job in both planning and operations to be consistent, because one result cannot be different for the other for a same kind of situation. So, and that's happening pretty soon.
Thank you. Alexandre?
Yes, I think I agree generally that we have the software. What we need is to get better in terms of models, because the modeling requirements for this kind of thing, they have to be consistent. But when you're doing a 20-year planning study at a 20-year timing horizon, any kind of gets is like, you don't know exactly which kind of manufacturer you're going to have. You don't know which kind of technology you're going to have. You don't even know if the technology within 20 years is not going to improve dramatically, and you may have different capability. But you have to make your decision now. And as you progress through this kind of decision, now you've chosen your manufacturer, so you know a little bit more about the kind of technology you need, but you haven't done the actual field study. You don't know the parameters, you don't know this kind of thing. And as you approach this kind of thing, you get more and more detailed model, and up to the fact that sometimes you get an actual model of the actual control system. And if you want to go any faster and any further because of interaction, you may actually buy a replica of the actual system just to look at the way it interacts with nearby system. That's the part that we don't really completely have now. The software we have, I think the data we have, I mean, it's besides the CID requirements, it's under the confidentiality questions and everything. Where we need to make headways is on the availability of models and the way our industry comes together to build these models. It's everybody perhaps in this room knows that we use a lot of these IEEE models, for generators. They were developed back in the 70s, and everybody collaborated on saying, well, what is the right way to model a generator control at different horizons? Well, we need to come together and actually do that. The problem is the technologies that we're dealing with are changing very rapidly, and so we need to go faster on doing this. And so that's what I would say, that having at least an open library of models, and this is something you understand that where say the Linux Foundation would be a strong way to actually do this in partnership with many other organizations. This could be one of the requirements there. We already have a set of open source tools that are really well suited for this. So I will mention a tool called Possible that does power flow, and it's implemented by RTE, it's implemented by Tenet, it's implemented by others. There's a lot of, it's already on industrial tools. There is a tool that's called Dynamo, and it allows you to essentially run different versions of models depending on the kind of phenomena you want to have, whether it's short circuit current, voltage stability, transient stability. It's a Modelica-based kind of thing. You describe the kind of modeling you have with the different requirements, and then it runs different engines in there. So the tools we do have, what we need is the effort to build together with the vendors different modeling and different modeling methodologies that capture the kind of thing that we want to capture, all the way from planning on a 20-year horizon to actually real-time systems in a consistent way.
Okay, I think we'll just go down the line. Thanks.
Actually, Alexandre said most of what I was going to say is that I think that we have, as we build these digital twins, we have the tools that we're going to need for the operators to really use them effectively. But I think there's the opportunity is in the planning side and seeing these models and getting the verification that the models are correct will help a lot in terms of being able to run quicker planning studies and more accurate planning studies. And there's actually a lot of speed to be picked up there.
So I want to key in on some of the modeling. A lot of people have discussed that 20-year, 10-year, your long-term planning type modeling and getting that accurate, which is critically important. As I see some of this being implemented, I see a challenge on a shorter time horizon. When you go from in real time, we're constantly working with our EMS vendor to better model various versions of these technologies. We're working on our implementation of AARs and what that looks like and how it integrates. Like, that's constantly under development, even with our outage management software and things like that. But a lot of that funnels down to real time. If you start applying, moving from that real time world and backing it up for an OPA assessment for tomorrow, your outage coordination for the next week, your outage coordination for the next 6 months, some traditional ways of thinking about things where you take like a seasonal peak model or whatever, I think are no longer adequate, or you're no longer maximizing the benefit of these technologies as you implement them. So the ability to move from that real-time model and have consistency across your power flow software, your VSAT, TSAT software, your outage management systems to plan the grid in that 0 to 6 month time frame, to maximize the benefits that you can get out of these technologies, is something that we're working on, and is a challenge, to bring it all together in a cohesive way.
I was going to stick with Alex for a second. I guess as these models are constantly evolving, is it somewhat inevitable that everyone's going to be using a different model, or is it like there's only a couple of vendors, so you wind up sort of sourcing back to the same type of model, albeit with differences?
Internally, so I think inevitably you start using a lot of different types of models. Different softwares use different model formats, and something that we're really trying to develop at SPP is kind of a single source of truth concept, where you always have something to go back to, whether that be a planning model time frame, or in the more operations world, always being able to source back to that real time model that's actually in production. The less variance you can have, the better. It definitely makes it easier to point to, but you have to make that work with all the different software types and different vendors. So it's a challenge. I don't know that I have a good answer for it, but
yeah, fair enough. Thanks.
On the operational side, am I going out of turn? Is it okay? On the operational side, there seems to be somewhat of a small wealth of software vendors that will help to integrate GETS. Most of the EMS vendors have options. The different vendor companies have options, as well as separate software companies. But as mentioned already, on the planning side, there's a lot of deficiencies in the planning software. And an example of where that somewhat leaves gaps is it's one thing to somewhat be reactive to say, okay, on the bulk electric system, there's going to be congestion, so we're going to deploy GETs. It's kind of proactive, but it is somewhat reactive because the problem, you're already staring at it. If there was better software solutions that would, say, match load profiles of interconnecting load customers and profiles of incoming generators, especially renewables, and then you could, in that same planning software, model what the DLR may look like, we could start to become more proactive with maybe using GETs for interconnections more than we are already, or to accommodate new generation, interconnections both ways, both load and on the generation side. That would be facilitated. What that looks like now for us is we create our own scripts within our planning software, or use AI to create them, with just expanding our own Python scripts and running different scenarios and studies. But it would be great to see more vendors play in that space, because we think we'd be able to be even more proactive with GETs.
Okay, let's move to Saugata, and then Emilie, and then Alexandre.
So I think just carrying on from David, what you just said, I think again, the good news is we have solved that problem. So we actually take into consideration the load interconnection, the generation interconnection projects at the same time, and what kind of GETs models can actually be modeled, and it's all automatically done with the software, and it comes up not with the models but also with the optimization of the grid using those models to kind of fast track the interconnection of load and generation as well. So that it's way better than Python scripts. So we are doing that already with our customers. Now coming to I think one of the points regarding the GETs modeling that was made, like Alexandre, I think you made a vital point. So the way we can actually solve that challenge of changing of the models across time and across different hardware vendors is the interesting part is here. The impact of the grid, when we are doing the studies at the system level, when we are doing the planning, for example, we are looking at system level impact. That impact is actually driven by the physics of the grid. So whichever proprietary model a particular GETs device may have, but the impact of that is a certain change in a parameter in the grid. As if we are able to model that physics-based deterministic kind of a behavior correctly, which we are able to do right now, even if you do not know the exact proprietary details of what is happening within that GETs device, we should still not have a detrimental impact on how we study those impacts when we do a system level study. So that's how we are addressing that kind of a challenge. So the inputs and the relationship between the inputs and the outputs of the GETs device could be proprietary, but the output impact on the grid, that's a physics. That's an impact of a certain change of parameter, and there are only handful parameters in the power grid model that can actually change. So that's how we are addressing that problem.
I think from an operational DLR perspective, the software is their integrations into EMSs are not easy and not fast, but a relatively known entity, straightforward API endpoints, things of that nature, where it definitely, to echo what David said, where it's definitely less clear, I think, is on the planning side. There are multiple systems, from a utility perspective, it's different groups, so there's a silo component there, but different software, different ways of integrating into those systems. And if you go with a full GridAstra style solution, you can get all of that in one place, but in some cases that's duplicative, or there's proprietary software that's already been built internal to the utility. So it's not necessarily straightforward in the way that the EMS is, and I think that has a lot to do with just maturity of the integration, but I think there's more ground to be covered there.
Yeah, I think to echo this again, if we were able to determine an open architecture for all of these software components with a way to have standard APIs to do that, I think we could achieve a lot of this plug and play kind of situation in which you make the entire thing modular, And so you can use proprietary software in each of the blocks, but because you have standards to do this, basically you can integrate and you minimize risk of this IT system, and you allow different vendors to be used actually in different situations. So I think there's a lot to explore this there, and again, other industries have been doing this. So I think there's a role here to play. I don't know where the impulse to do that could come from, but definitely this is something possible, and that would alleviate a lot of other problem. I still want to leave I get the impression that we gave an answer that's a little bit out of what you were perhaps expecting here, because I just want to make a comment on digital twins and analytics, just stating, and perhaps you're going to echo this, there's a lot of potential for AI solutions to help us quite a bit in this. So we see a lot of projects and pilots. They're at the stage of pilots where you can use essentially AI tools as assistants to help the operators manage the increasing complexity in the system. And so we see all this kind of thing being developed also in terms of foundational models for very long-term studies. We also see very innovative startups looking at ways to optimize the interconnection process. So because there's a lot of things that you can do with AI to do this. So we've taken the kind of, well, how do we navigate the existing ecosystem and try to use Get effectively there. But there's a lot coming down in terms of new software improvement. I think perhaps tomorrow we're going to hear some of this. So I wanted to end with a more positive note,
Great. And then can we go to Michael?
Yeah, I guess I would just say, with all these solutions, we kind of already said it, right? But if there's 5 different solutions of 5 different grid enhancing technologies and digital twins, it's really hard to manage that as a real operator in terms of real time. It really needs to be in one unified system. And so that's what we have. Hopefully APIs and can do integrations, but it's unrealistic to expect a system operator to swivel their chair to every different system to find a different solution for a different problem. So really we have to have one sort of source of truth in terms of like the real-time conditions of the system and what options they have for their system. In terms of planners, they're an interesting group, and if you met them, they know they like as much data as they can have. They want 20 years of data for something. And so when we're trying to talk to them about, hey, can you use grid enhancing technologies in your planning, it's how much data can you give me? And you give them, I have a year, 3 years, or 4 years. And it's a struggle to kind of get them comfortable with that, to use that for long-term planning at Great River Energy. And because it's different, but also they don't have all this data, and the data can be so dynamic and so all over the place that when you're trying to plan for worst case scenarios, it can be when you're trying to plan, when you're trying to build a robust system, and you're really building first and foremost for reliability, because really, there's market functions. We're building for reliability. We want to make sure that we're not going to be overloading our system. And so when you have grid enhancing technologies, it sort of changes that whole approach and whole equation. And I think what my peers and different people I've talked to are still trying to figure out the best way to include things like grid enhancing technologies as part of a planning model. I'll leave it at that.
Thank you. And then I have a follow-up question just for the group on the capability of accepting DLRs. What does that look like? And is it a matter of course, or are the RTOs expanding on that?
Well, I was going to talk a little bit more about the operator's ability to accept these technologies. So, as you start to build these digital twins and have more real-time analytics, I think you can actually speed the deployment of new technologies that maybe aren't even out there yet. So, for example, when a new technology comes and we're looking to try it out, maybe it uprates a line. So there's a couple companies right now making technology where you can coat your existing conductors, and they claim that you can get additional capacity out of that. It's difficult to know how much you actually can get out of it. So these digital twins, the real-time analytics, will allow us to actually measure and verify that and more quickly adopt these technologies to see that they really do work. And then use that to improve our planning around it. So I think there's future benefits to these that will help with that adoption.
Does a digital twin then like give you a better benefit to cost assessment?
Yes, I think it helps with understanding how much benefit you're actually getting from the new technology. So when you pilot something new, you can more quickly see the benefits and then more quickly measure those benefits and determine if something worth scaling or not. And then the operators who are seeing that will more quickly, from a cultural perspective, be ready to accept those benefits.
Go to Emilie.
So on the question of DLR adoption into software, I mean, I think AAR moved us ahead quite a bit in terms of that adoption. It's hourly data. It's very similar, especially for an EMS integration. Where we have seen maybe a double click on integrations is, I'd say, around weather. So we've had some utilities ask us if we can use their weather data instead of ours. In theory, yes, there is some trickiness around the proprietary models that we have and how we're converting that data. But that's definitely something, getting back to a couple of folks have talked about, a single source of truth. So having the same weather that is underpinning all the assumptions in utility operations. So that's something we're looking into. Also, weather stations. So we have our own sensors, but a lot of DLR is dependent on wind. So if there are weather stations already deployed, utilities in California in particular have thousands of weather stations deployed. How can they leverage those? How can they stack value across multiple use cases to amortize costs there? So those are areas where we are seeing more of kind of a deeper view on integration.
Yeah, Michael.
I'll just say for our DLR deployment, directly for your question, so we're getting the data into our EMS system for a real-time system. We're sending it to MISO real-time via ICCP right now. So we're sending them data every time it updates for our system. For AMI-adjusted rating, as Emilie said, that's moved things along really nicely because the same software to accept these ratings for AMI-adjusted are going to be the same software, it's my understanding, to accept dynamic line ratings. So real-time, we can send the data today. There's in the MISO model, in our case, you can basically find little slots and say real-time, short-term, long-term emergency ratings, configure it, and you send it to MISO. For the forecast data for AMI adjusted ratings, we're going to rely on MISO to do our forecast for that, even though we're getting the weather data back from them to do like real time. But so for the forecast, I expect the same thing though. When the AMI adjusted rating is available, once it's fully deployed on the software side, so the EMS system of MISO, then there should be basically the same thing where there's data terminals. You can basically put the data in there and you can send them your forecast data. So for us, I guess the holdup not the holdup, but we're using dynamic line ratings real time, but we're not using them day ahead or forecast just because we don't have an easy integration path that I know of right now with MISO. So I think it'll come naturally. It's just a matter of the software, and big systems take a long time to get developed. So.
I have another question, but colleagues, did anyone follow up? No? All right. I think the next question is around infrastructure and what we might need. I think sometimes we talk about a software-only solution, or sometimes it's very obvious it's a, somewhat of a physical solution, but what type of infrastructure do we need to deploy more GETs? You could kind of take that any way you want to go with it. It could be anything from advanced conductors to a DLR, but or even the sensor versus sensorless discussion. What kind of infrastructure do we need to get more GETs on the system? I see David first. Thank you.
Sure. So related to advanced conductors, our view on it is when you look at the different options, there's almost a spectrum of advanced conductors and different technologies. So for us, like if you go back 20 years, the conductors that are our current standard and spec that we put up in the air have more than a 20% boost of what we used to. Then if you go to the extreme end of the spectrum, you might get into technologies where when we present different concerns like ice loading and unique hardware specific to that conductor, we're trying to look for the vendors to somewhat kind of step up with some of their, like, backing up some of their claims with, like, warranties and things like that, because what we worry about is we don't want to dive into a technology and then have to touch it again 10 years later because it stretched during ice loading and the steel medium didn't stretch before, but the plastic, the polymer does, things like that. And so we move in. What we're trying to work with the vendors more on that, but from an infrastructure perspective, actually, Andrew, a lot of what he said earlier about advanced conductors is our view on the application also. It's like a tool in the toolbox. When it comes to infrastructure around some of the other, I'll say, like, smaller, less expensive technologies, we already have a system blanketed with SCADA devices, monitors, transformer monitors, circuit breaker monitors, reclosures on distribution. The new GETS technologies looks very similar in path. The communication protocols are either cellular or a mesh network, or if you can get to the sub, fiber back. The same typical firewalls and protections from a cybersecurity perspective. So, like, infrastructure spend for, like, the smaller GETS technologies, from our view, is nothing out of line or very minimal to what we typically do. It's the advanced conductor types where you're kind of thinking more of, like, your traditional infrastructure and what it looks like when it comes to spare equipment, ease of installation. If it's just the reconductor, do you have to change out poles, or do you have to change your span configurations? Can it handle the same wind speeds and ice loading and things like that, depending on your jurisdiction? In Kentucky, we might be more prone to it. Up in Rhode Island, maybe not so much. So it just, you're taking in different factors when it comes to those types.
Does that kind of come out in GETS or just transmission planning, or is that just a false dichotomy?
Yeah, that's a great question. I would say we keep as much as we can with our planners. Even if it's going to impact real-time operations, we try to have the planners doing the evaluation on it, because they're not just looking at it from a technical perspective, but they're also looking at the benefit to cost ratios and the maintenance impacts and things like that. And so for us, it's with our planning groups.
I somewhat lost track, so I'm going to go down the line. Saugata next. Yeah.
Yeah, I think when it comes to leveraging the existing infrastructure that we have, I think I kind of agree with the statements made so far, because GETS is such a thing that it's such a nice thing, in fact, which is you use the existing infrastructure to increase the capacity of the existing infrastructure. So that is kind of, in a nutshell, what GETS can do. So, for example, when it comes to things like topology optimization, again, it's a purely software-based approach, and like I mentioned earlier, as long as we are kind of in sync with what the devices are there in the substation, which you can model, and you can actually tell the software to just do things that are practically feasible, it can easily come up with that kind of a topology optimization using the existing circuit breakers and switches in the substation. When it comes to DLRs, like if we are, for example, using a software-based DLR, we are creating a digital twin model, so it really does not need a lot of infrastructure to actually support a software-based DLR computation, and you can scale that across the system. So that is with respect to the DLR. Now, when it comes to even the power flow controllers, a similar point that I made earlier was software can actually help figure out which are those substations that you may actually want to use or reuse and expand to have a power flow controller also installed. Which are those optimal locations, so that with least number of such substation expansions that we do, we can actually derive the maximum benefits out of it. And fourth is, for example, like we talked about the advanced conductors. Now, there are places where you can use it, and there are places you may want to use a different kind of a network upgrade. So again, that is where software becomes pivotal, because it can actually kind of adjust to your needs, that okay, if there are certain places you do not want to use advanced conductors, mention that to the software. It comes up with another type of GETS or a combination of GETS and conventional kind of network upgrade. And places where it actually is possible to use advanced conductors, let's use those. So I think that is again where, if we can reuse the existing right-of-ways, if we can reuse the existing tower structures to the maximum kind of possible extent, that actually increases the utilization of the existing infrastructure of the grid. So that's where, again, software can play a role when you're doing the planning.
So just if I could restate, just so I'm understanding you correctly, for things like topology optimization, essentially no new infrastructure, but it might help to identify where you could, I guess, best deploy additional infrastructure.
Yes, you could use it like that as well. Yeah.
Where you're going to get the maximum benefit to cost
Absolutely.
ratio.
Absolutely.
Okay. Thank you.
Yeah, thanks. So I guess for us, I'm just not going to talk about DLR because I feel like we covered that. But the other ones, we have a StatCom up north in northern Minnesota, replacing some generators that retired. So in terms of infrastructure, that's another transmission project, but that is not necessarily cheap, as cheap as some of these software-based solutions. So if that's considered a grid enhancing technology, that is something to consider. For advanced conductors, the way we've been looking at it, so the high temperature, high tension, low sag for advanced conductors, we've really been trying to find places where it makes sense to use it, but it's more expensive than traditional conductors right now. And so the places that we would really use it, especially where we are in Minnesota, is over rivers, over lakes, over where we need a long stretch where it's much harder to put poles in a water, in a lake than it would be to have a high conductor. So where there's a couple opportunities we found, but as long as there's still the 2 or 3x or whatever it's going to be, depending on each use. As long as the price is significantly more for our membership, it doesn't really make sense just to do that yet. One thing we are considering, and hopefully others are too, is to build new construction towers, for example, to the point where they can be updated and rewired or reconducted with advanced conductors. So it's something where you can use traditional conductors now, build your poles for the next thing, the future. At some point, that could be a lot easier than to rewire them if you could use the same right of way as you had before. So there's some sort of future proofing you can do. They do make sense. Some places it's just for us in our system. There's only a certain handful of places that have made sense so far. The other thing I'll talk about is we use Prisma I mentioned before, which uses a fiber as a sensor. And so when we build all the lines we build now, we add OPGW, which is the ground wire on top of it for communications, a fiber wire. So we add that to all of our new builds. And what they do is they leverage that as a sensor. So they basically can use that. They shoot light down, it reflects. They can basically use it to measure things like wind speed, detect wildfire. We originally installed it for reliability reasons. So if we saw we had a car crash, hit a pole, but didn't cause a fault, for example, we wouldn't have known about that till the police called. But if we have the system, it can actually pick that up right away. So we started with reliability for them. We're using some dynamic line ratings, but the advantage and the reason we like that, especially, again, for our membership, which we're always trying to do right by, we already have the fiber. And so for us to install that, since we already build the fiber up there, it's literally installing servers in a substation, plugging the fiber in, and all of a sudden you have the sensor. And it's something we mentioned earlier, that sensor runs across the entire line. So it's every span. So with the sensor, we have both. We have sensors. We have some software-based solutions. We have Prisma. But that critical span idea is one that is real. And so sometimes when the fiber is on the entire span, you can detect every span, every part of it compared to the sensors where there's an engineering study to it. But to bring it back, having that already installed made that infrastructure a lot easier to do. And it's harder for us to think about if we would go out and install fiber everywhere to install that solution, or the fact that we already have it made it a lot easier for us. So maybe a takeaway is, even if you're not using them today, you can future-proof for a lot of these things coming down the line that you see from 5 years from now.
It sounds like the technologies are additive.
Yep, exactly. So, so Prisma and Heimdall, which we use, they both can do dynamic line ratings, so you can use them together. And that's why another reason, since we have so many different things, we want that single source of truth for the operators. We want them all to come into our EMS system. But yes, we're using we have different lines that have Prisma compared to Heimdall to monitor different things, and then like our StatComs and our software solutions. It's sort of all over our system. It would be probably more productive if it was our entire system. Some people have mentioned that if you have the entire picture, you can actually maybe do more with it. But again, where we are, we're very interconnected to our neighbors, so we would have to work with Excel and other utilities to kind of make that happen. But for us, yeah, we're using them all at the same time together to try to make better decisions.
Yeah, thanks again. Emily?
So I'll touch on the sensor versus sensorless solution space. And, I definitely echo the comment around getting kind of the network-wide view. using the sensorless solution. It's very fast to scale, it's very fast to get insights and grid intelligence. What we have found is it's also a really useful way to identify critical lines. Utilities have a pretty good understanding of where their congestion points are, but we're able to use that sensorless solution to look for areas maybe where there's vegetative shielding that is causing a line to be more constrained or a span to be more constrained, and that can actually guide where the sensors are placed and where we are more reliant on that ground source of truth. The other thing I'll say is with our sensor solution, we are able to capture maybe some ancillary benefits. So having a camera that's pointing at the line, we can look at sag, we can look at icing, we can look at galloping. We even have had some customers ask us about wildfire mitigation. It's obviously not eyes on the whole network, but if there are more remote areas, having that imagery directly from the right of way can be extremely helpful. So it is kind of a stacked benefit component there to include the sensor.
Looks like Andrew is next. Thank you.
Yeah, I think at the core of it, what the gets are all about just getting more out of the existing system, and so in a lot of situations, the existing system is going to dictate what the right gets is to use, right? So if you have an old line that's going to have to be rebuilt in the very near future, you're probably not going to use an advanced conductor. You might use DLR, you might use power flow controller or something along those lines. But also there's that element that Michael touched on, which is future proofing, right? So when you do rebuild a line, you're going to want to build it so it meets today's need, but it's also a cheap, easy solution to maybe get an extra 10-15% out of it, or maybe 50% with an advanced conductor. So you want to build it for that future proof as well. But the existing system is going to kind of dictate what you can do.
I guess if you have an old line that you don't want to rebuild, is it that eventually you're going to replace the whole line, but then you could replace the whole line and still use an advanced conductor material, or?
So it's going to be individually engineered, right? So if you're trying to get something connected quickly, and you're doing it on a line that has maybe 10 years of life left in it, you are not going to string new conductor on that line, because you're going to end up rebuilding it. So you got to make the choice. Am I going to rebuild the line now? Am I going to use DLR? Am I going to use a power flow controller that might be able to, sort of reroute the power so that there is more capacity on that line in the short term? And then ultimately down the line, I end up rebuilding it, right? So you're kind of thinking both short term and long term with these. They give you more options in terms of the timing of actually implementing it. You're not everything is a construction project immediately to serve the long term.
Yeah, thank you for that. Michael, again?
Yeah, I just wanted to add one example, which I think is interesting. So the first line that we put dynamic line ratings on, it was a fairly new line actually, and we had rebuilt it. And then what happened is several facilities away, some wind farms were installed. And then what happened is during the interconnection studies, they did the study, everything was fine. What happened once the wind farm came online is that our line ended up being one of the lines causing the congestion in the area. And so this is a line that's not that old. And so we don't really want to rebuild it. And so that was a really good case for us to say, well, if we put dynamic line ratings on there, potentially we can get more benefit out of it, because again, it's congested when the wind blows. And so that's one where if you, like you said, these are all kind of tools in that toolbox of looking at every individual example. But that was a really good example for us, because we have software to model congestion. We use ProMod, which I think other utilities do too. So you can model congestion, see what's going on with it, and then kind of find a good way to do it. But for that one, since we didn't want to rebuild it, we didn't want to read a conductor at the time several years ago. So it was kind of one good example where that made sense just to put up those dynamic line ratings, because we modeled that we get a lot of benefit out of it.
If I can follow up with you, recognizing you're a cooperative, like, when you make that decision, is it a business case decision, or is it, at what point is MISO kind of brought into the fold, or even the state of Minnesota, or when you're kind of saying, hey, we're going to do this in lieu of that?
Yep. So I think Great River Energy made the decision. And so for that one, with that congestion, we could model that congestion. We can model the economic impact to it. And so that was one where, for some of these things, they're reliability, some are more congestion markets, some are both. And so in this case, it was causing curtailment of wind farms, and it was causing congestion of wind farms and load, or I guess the wind farm too. So really what we did a kind of a business case for economics on this and looked at it and said, we know the last year it had this much hours of congestion. Here's, if we would have gotten extra 10%, 15%, 20%, what would that look like in terms of the benefit to Great River Energy? So it was mostly a decision that we made, and then after that we go, it's part of our plans that we'll put out to the Minnesota State, and we'll talk to MISO about, but we made the decision to move forward with this technology sort of without input, I guess, from them, or being told to do it, I guess. Yes. Maybe I'll leave it at that for now, unless you have follow-up questions, but yeah.
Yeah, I'll probably ask as many as you'll indulge me on,
Yeah,
but
you gotta talk about it.
I guess in some scenarios you may or may not own that wind farm, and so if you relieve congestion, I would assume it's to their benefit, at least in part, and so many of these benefits seem to straddle, I guess, artificial seams, for lack of a better term, and part of what we're trying to understand is, how do you accurately measure those benefits and then assign them?
That is very true. And so again, I think Great River is a little unique because we're so interconnected. And so we have lines that are one of ours, another utility, one of ours, substate, whatever. So when we're looking at this benefit, there's sort of two things we looked at. One is the market benefit. So one was the MISO benefit to everyone, and then one was Great River Energy benefit specifically. And so for us, we knew, because in this case, we are buying the output of the wind farm. So if it gets curtailed, it does affect us, and we have load on the other side as well, a little bit ways away. So we can look at it. On our studies, the benefit to the MISO market is significantly higher than the benefit to GRE. So it does benefit other people doing it, but it was a good decision also for us to put in these sensors. But you are correct that especially for some of these market things, congestion can be hard to model, can be hard to pin down. It can move congestion. You don't want to move it, you want to relieve it. And so there's sometimes where it can impact other players, I guess, other stakeholders when you're looking at how to relieve it.
That was it on my questions. Do you have another one?
Yeah, I kind of want to roll into a different topic. So we've heard from a lot of you that you are deploying DLRs to different extents and other GETS technologies. I wanted to understand, are you considering broader deployment of any of those technologies, and why or why not? And we can start with David.
So the definite answer is yes. And when we've thought about that and planned that out, we actually did look to Europe for benchmarking. We picked on the country of Belgium. The utility there is Emilie, and they have DLR on most of their bulk electric system. And so we actually just did some benchmarking of what that looks like when you have, I'll say, widespread use in your own system of dynamic line rating specifically coming in. And in that benchmarking, I mean, it almost seemed like we walked away with what we felt like in the beginning, even if you have one installation. There's always complexities, you face them head on, but they're definitely achievable and everything can be overcome. When it comes to the other types of technologies, we're evaluating several other ones right now, including leveraging our fiber system. We have fiber to every substation of our transmission substation, so it's like some of the existing infrastructure, including communication, could be used. But for us, widespread versus just pilot, really not much of a difference. It's the same challenges to overcome, and once you overcome them, then it's another part of your system.
Go to Andrew and then Michael.
Yeah. So we're also doing a widespread deployment of DLR, and the reasons, there's a number of reasons. So for one, FERC Order 881 required the TOs to implement ambient adjusted ratings and integrate that with the ISOs. So from there, it's not a big jump to implement DLRs and integrate that with the ISOs. At the same time, we just happen to be upgrading our EMS system, so it's the right time to do those integrations. And then we feel that by building that digital twin, we will have that measure and verify capability, and we'll be able to deploy additional GETS technology quicker by having that visibility onto our system. So, and at the same time, we've been doing a lot of research and work with our control center operators in terms of sort of how do we culturally deploy this so they're more ready to use it. So those things are all kind of coming together for us. So it's a good time for us to deploy it, and we think that by deploying it widespread, we'll get that benefit.
Yeah, I would definitely echo that. Having DLR in the system and then expanding more DLR is not really that big of a leap. And I think AAR did help us get in position to that and probably get the ISOs in position, RTOs in position to do that as well. So for our system, what we're looking at, we have some congestion tools I mentioned. We use ProMod as a software to look at where we have congestion. And so we're open to more gets, we're open to more evaluations, but for us, we're kind of trying to find areas where we actually have congestion and trying to relieve it right now. So we have about 10 lines about 200 miles or so of dynamic line ratings right now. And anything else that we would do on our system for dynamic line ratings wouldn't actually have a benefit to us or our membership, either because the facility rating itself is the limiting factor, so like a breaker, or switch, or a jumper, not actually the conductor, or we might not own one side of the line because we're interconnected with our utilities. So we, at this point, if we deployed it, it would be a cost to GRE and our membership, and we probably wouldn't get really any benefit out of it just because we don't have that congestion. If we had more congestion, I think we would look at DLR for a potential solution for that. Again, we aren't always looking at DLR as a replacement for rebuilds either, and so depending on the situation, maybe it's something that's just in our natural work plan to rebuild some of these lines if we do that, or if we had some sort of something new that caused congestion, we might have to look at building lines rather than DLR. But in terms of I don't think we would deploy, for example, dynamic line rates on our whole system at any point, unless it's required at some point, just because the cost would outweigh the benefit. We are looking at some other things like the fiber monitoring, which, for a grid enhancing technology, not necessarily DLR, but that sort of provides some reliability benefits and some things for mechanical hits or electrical issues or wildfires. So we're looking at maybe more of those type of reliability things for our membership rather than the cost saving type things. But yeah, I think for us, we're always considering DLR where we have it. We're always looking for it. We're looking for temporary congestion with construction projects. We really are looking how to minimize it. But we're kind of doing all that without at this point regulation or being told to do our entire system, which would not probably make sense for us right now.
Okay, can we go to Emilie?
So I think there are two maybe step changes that happen in terms of adoption. One is going from pilot to more of an actual program or project, and the big barrier there really does tend to be around the EMS integration, getting operationally integrated into the utility. From there, I think it has a lot to do with new use cases. So where we've seen expansion is often around, for example, congestion related to new load interconnects, congestion related to renewable curtailment. We have several utilities who are trying to get offshore wind into their network and move that effectively across their grid. So that's where we start to see okay, this is proven technology. Where else could we use this tool? And as Michael said, it's typically not just it'd be, on the planning side, maybe they would say, give us all the data. But from an operational standpoint, there does need to be an actual defined use case, a pain point that's being addressed. And that's what's really driving the expansion.
Okay, we'll go to Alex and then Alexandre.
Yeah, I mean, just as far as a broader implementation of these technologies, I mean, we've talked a lot about dynamic line ratings, but there's a lot of options here. So I know at SPP, we're currently in the process of setting up an intermediate planning team. And the goal of that team, I think, will ultimately target a lot of these types of technologies. So out of our longer term planning processes, we just our last transmission portfolio was the $8 billion portfolio. It was the largest one we've ever put out. We fully expect our next one to break that record again. But what you see with a lot of those is just the time it takes to put all that steel in the ground. where we're definitely wanting to support our members and the utilities under us for like looking at that, 0 to 5 year mark, 0 to 8 year mark to build the transmission. And there's a lot of benefits there, whether you've already identified the need and we're going to build larger infrastructure, but it's already showing up in real time. So we kind of have to do something in the meantime. And we're trying to set up processes to implement some of these technologies to mitigate that while not, quote, covering up the need for that longer term infrastructure. And that's bridging the gap to longer term projects, or even just the freeing up megawatts from renewables that are being curtailed, or mitigating congestion from natural load growth, large loads, whatever it may be. There's a lot of opportunity there, and we're trying to look at that, next 0 to 5 year look to implement stuff to mitigate it.
So I guess completing a little bit of what's being said, I think like deploying gets everywhere. I mean, it depends on the kind of gets already, and then there's a little bit of different aspects to this. For example, for transmission switching, if it has benefits, if the only cost to this is just a little bit more wear and tear on a breaker, I don't think that you'll find any. You'll think that the benefit just completely outweighs the cost, and so there should be no question. Even if you have to make these switching elements controllable, and you have to input a few sensors, I don't see why the cost benefit should tell you this is something good. I guess on the extreme side of this, nobody in a reasonable mind would say let's put STATCOMs everywhere. And that's we're already actually seeing a little bit of a more lead time in actually procuring STATCOM, because there's also a supply chain element to this. There's a supply chain element to advanced conductors. So perhaps also it's deploying everywhere may not be the best kind of thing. And in the case of a STATCOM, if somebody tells me, well, we have to install a STATCOM because we cannot require some of the IBRs to actually, or even data centers, or to provide some kind of voltage support, and so we have to install a STATCOM because they cannot do it. But optimally, that would be the best solution. Then I don't think the STATCOM is the optimal way to do that. Now there's a lot of questions to this, but basically you have to agree in some cases that installing gets everywhere and indiscriminately is not the right thing. And then you have this kind. I mean, we talk a lot about DLR. I'll just say from a European perspective, there are some system operators that decide to install them very broadly. Again, because there is not so much of once you've installed a few and your system is really good. I think most of them have decided to use them where there are actual use cases, but making sure. And I think that's the case pretty much everywhere, that the system is ready to welcome any kind of DLR. Now, provided that there are different technologies, so we're not completely I think we still have some room to improve in terms of establishing standards on how to actually communicate with the system, and we touch on the system integration. But I just wanted to highlight, there are things where developing everywhere just like is a straight cut benefit analysis. There are situations in which it's not, and we should definitely not go there. And there is this kind of in between.
I guess at least with respect to DLRs, I thought I heard two different stories. But on the one hand, I heard if I have a pilot project implementing DLRs going system-wide, would not be a heavy lift. Then on the other, I heard, but probably the benefits to cost, excuse me, you know what I'm trying to say. The benefits would not outweigh the costs. And so I'm just trying to reconcile those two things. It's not a heavy lift, but it probably doesn't make sense system-wide, or did I mishear you? Sure, I'll start with Michael, I guess.
Sure. So I guess what I mean is that, and so if we have whatever 50 sensors installed right now, if we wanted to install another 100 sensors or 200 or whatever, the processes and integrations are all completely defined. So installing these sensors is easy from the fact that once the sensor's up, it goes through the same path right now. There's some, but it'll get to mice and we'll see the benefit. There's still cost to that. There's still effort to do that. It's just that the integration, which is probably the hardest part, is already finished. So we still have to pay money, real money for the sensors, for subscription costs, for labor, for for other things to do it. And so what happened is we could put these sensors up on our whole system. We could do it over a period of time. 90% of them our lines are not congested today. So if we get additional 10% capacity, that doesn't matter. That doesn't help anybody, I guess. But we have to pay for that. And so then, and our membership really. So there's a cost where we might spend whatever that amount of money is going to be, and it wouldn't be that hard of a lift to do, but economically it wouldn't actually benefit us at all. So it's just an extra cost of, how much ever that's going to be every year we're paying to not get any benefit because we don't need any benefits. There's no congestion on all of our lines. So that's where I was coming from.
Yeah, thanks.
Can I add some color to Jesse's question? There are different types of DLR, and does the answer to his question depend to some degree on whether we're talking about sensor-based DLR, sensorless, or digital DLR? Emilie?
So I think it definitely does. I will say where we are seeing more of an expansion opportunity, whether it be with sensors or sensorless digital DLR, however you want to describe it, is getting kind of beyond just the congestion use case. So what other grid intelligence can we tie into with that DLR data? We mentioned outage management, expanding outage windows. We are working with even some project developers who are interested in kind of going to a utility with a more complete package of, hey, we want to interconnect here. Here's some data that backs up, not utility proprietary data, but here's data that backs up our case to connect here. We're seeing utilities also looking at, again, more on that planning side. Maybe there is an upgrade that they want to make and actually make an infrastructure investment. How can we help them justify that and say we are, obviously affordability is a huge concern right now. So we are being judicious with our members or our customers' money. And here's the data that proves that we need to make this upgrade. And it's not as obvious on how you quantify that, but it is kind of I'd say a new frontier on the cost benefit analysis.
Okay, we'll go to Saugata and then Andrew. And then after that, we'll go to David.
Perfect. Yeah, I think when it comes to the question of scaling of the DLRs, I agree with Emilie here, because a lot of the scaling question really depends on the type of technology of the DLR that you're using. And we can actually relatively easily scale up the sensorless or the software-based DLRs without much of a heavy lift. And that can be done system-wide much more easily than the other type of gets. Now, coming to the point that Alexandre made earlier, like if we are thinking about moving from the pilot beyond and thinking about scale, not all type of gets technologies need to be scaled system-wide. Now, if you think about it, going like walking before we run kind of an approach after the pilots, we can actually find out that, okay, what are the different type of reliability or economic requirements that we have? What are the highest priorities beyond the pilot? And what are the minimum different types of gets that can be needed to solve those problems? And if we can optimally place different types of gets at optimal locations in the grid with optimal control set points, that is a question that can be answered, and we can actually derive the maximum benefits that we need with the minimum amount of gets deployment. That is again where software comes in, where it can actually tell you where those locations are, under what conditions you want to use them, what type of gets you want, what should be their control set points. That's the computation that a software can do, which is very difficult for a human mind to comprehend. If we can get that to happen, then we can actually start thinking about even scaling that more, only for certain types of gets that need to be scaled more. So, and all of this need to happen kind of in parallel with the conventional way in which the grid is getting expanded. So it's a massive co-optimization or a coordination that will need to happen. But there is definitely a way forward beyond the pilots.
So on the question of widespread deployment versus strategic deployment, it depends on the system that you have, right? So I'll juxtapose our UK transmission system versus our New England transmission system. So in the UK, where it's heavily congested, they had a couple of lines where they were able to put DLR on, get 7% additional capacity on that. It immediately allowed them to run additional generation that was less expensive, saved $18 million in the first year on that one line, which drastically was paid for itself in terms of that deployment. We don't have the same level of congestion in New England, but we have, for example, it's very congested when you try to take a line out of service to do construction, and it shortens up your construction windows, right? So if you're able to take a project that would be 2 years, which is 4 construction seasons, we construct in the spring, we construct in the fall, and turn that into a 1 year or even 3 construction seasons, cut 6 to 12 months off the duration of that project. Or maybe you can do 2 projects at the same time. That time is money, right? So you'll now be able to deliver that project quicker, get the benefit of the project sooner, and deliver it for maybe $10 million less, right? And that will pay for itself. So it's a different sort of benefits case, and depending on your system might be the reason that you're deploying it differently, and that's why we've chosen to make that decision in those 2 different places.
I'll just add, just to complement something that Emilie said, our predominant reason for using DLR does remain congestion, but one other secondary use case that we've used it for is when you look at our transmission system, we've monitored just about every major component: batteries, circuit breakers, transformers, CCVTs, all the way down the line. And we do that monitoring so that we can reduce maintenance and so that we can make better asset replacement decisions. We've really never had good data coming from conductors. And so that's somewhat of our secondary use case for DLR is it's a data set that we've taken and we've combined with our protective relay data set of how many faults that line has seen, et cetera. Conductors is obviously a very long-lived asset. So when you're going to replace it, it's could it last 70 years? Could it last 100 years? What is it? When you have data to back up your decisions, it makes it that you're not going to unnecessarily spend and that you invest at the right time. And so that has been a secondary use case for it, is basically conductor monitoring when combined with relay data.
Michael?
Yeah, and I actually echo that point too. That's one thing we're talking about Great River Energy is that everything in both substations is monitored completely. Why aren't we monitoring the conductor? And there's lots of different ways to do that with these technologies, but that's one thing that I completely agree with. What I was going to say is that I want to emphasize that I think utilities know their system probably really well. And I think utilities generally know where their congestion is, where their pain points are, where their construction is, what's going to cause congestion, where they need help, where they don't need help. And so a lot of times, I'll speak for Great River Energy, we're always proactively trying to find ways to do that, which is why we did these things, which is why we did DLR and we're doing these things. So the idea that, for example, we get a new software solution of a digital twin that says, hey, did you know you have a problem here? We're going to say, yeah, we know that. We're looking for ways to address it. We're rebuilding it or using advanced technologies. And so I think that it should be emphasized utilities generally know their system the best and know where they need help, and they're trying to find ways to address it. And GETS is a great opportunity to do some of those things.
I was just going to see colleagues, any follow-up questions? All right, Elizabeth?
Yeah. So before the break, one thing I heard from a number of you is that, you referenced different challenges or questions that have arisen around cybersecurity and use of the cloud. And I'm wondering if you can give a little more color on how that arose as you were going through different steps of a new GETS deployment, whether, in particular, if there are any lessons learned to share from those who may follow after you, and whether or how there might be whether there's a need for more clarity.
can start with David.
The biggest focus for us was it's a technology that we're going to use to actually change potentially how we operate our transmission system. And so the sanctity of the data is very important. The vendors, just to be complimentary, the industry of vendors for the GETs tends to be pretty flexible with what we'd like to make us feel comfortable with that data. So it tends to be data flows from the devices to the vendor cloud, and then the discussion comes around, okay, does it stay in that cloud? Where is it hosted? Do we bring it on-prem, et cetera? So for us, our stance has been, we're okay with cloud, but at any time, we want to be able to bring it on-prem, and we want full access to the data and ownership of the data, because we're using it to operate our transmission system. And as long as a vendor is willing to play ball with that, then we basically are comfortable, and then we apply the compliance standards and our procedures to that data flow.
Just to follow up with you, has that been the case in your experience that they are willing to play ball?
Yes. For all of the vendors that we've dealt with, yes.
Okay, we'll go to Emilie.
I think maybe to address your question of when does that come up in the process, we've had, I think the general trend is from a pilot perspective where you're not in the EMS, there's more tolerance of a cloud solution, a purely cloud-based solution. When you get into that EMS integration, that's where we start to see more of an on-prem type requirement where you're actually touching these secure systems. One maybe interesting new development has been one of our customers based on state regulations. They are now basically saying no CEII can leave their premises, which is definitely causing us to have to rethink how we are ingesting data, how we are building out models for digital twins, having to do all of that, maintain that software on site is certainly doable, but introduces some interesting new challenges around VPNs, having somebody actually physically on site to do installations and patches and things like that. So that's been, I would say it's a rapidly evolving space.
And just to follow up on that, are you guys seeing that the relationship between state entities and other things are somewhat complicating the ability to move forward with some GETS technologies?
I haven't seen the state necessarily being the blocker. I think in most cases, like I live in Colorado, we're seeing the state actually pushing the utilities to act. So I think it's maybe more in the other direction, but I won't speak for everyone.
We could go to Michael and then David.
It'll be quick. I disagree. So in Minnesota, we're the same thing. The state's very on board with GETS. They're pushing it. They're encouraging it. They're very active in what we're doing. They like to ask a lot of questions for the PUC and everything. So generally, I think this it's probably state by state. Minnesota is also very encouraging of grid enhancing technologies.
Same. We're predominantly in 3 states. We touch in 4, and all are proponents of GETS.
Okay, awesome. We'll turn it back to Jesse.
Well, unless anyone has anything else, I think that's the end of the questions. So we have load forecasting coming up in the afternoon at 2. Maybe we'll kind of reconvene about 1:50, but just give tremendous thanks to all of our panelists and their candor. We really, really appreciate it, and thank you all.